Uma nova era de conectividade está em movimento. O 5G transforma o presente. O 6G define o futuro. As conexões encurtam distâncias e revolucionam a maneira como experimentamos o dia a dia. A internet das coisas ganha vida e mexe com os nossos sentidos. Dispositivos se comunicam, homens e máquinas se conectam, cidades inteligentes emergem e o campo se integra a esta rede. O XG Mobile lidera essa transformação. Nossa missão: ultrapassar as fronteiras tecnológicas e atender às demandas de um mundo hiperconectado. Unimos a pesquisa acadêmica e as necessidades da indústria. Pesquisadores e especialistas dedicados transformam as ideias de hoje nas conquistas de amanhã. Oferecemos uma imersão no ambiente científico e tecnológico, laboratórios modernos e uma robusta infraestrutura prontos para a criação do que está por vir. Preparamos as mentes que guiarão essa revolução digital. Com programas de iniciação científica, pós-graduação e cursos de curta duração, formamos os profissionais de agora e das próximas gerações. Conectamos empresas, startups, centros de pesquisas em uma rede global de inovação que fomenta competências e impulsiona oportunidades. Somos o centro de competência Embrapi Inatel em redes 5G e 6G. Somos o XG Mobile. Juntos, criamos o futuro das comunicações móveis hoje.
Bom dia a todos. Bem-vindos novamente ao nosso segundo dia do workshop do XG Mobile. Hoje nós vamos ter um dia bastante interessante em termos de tutoriais. Serão 2 tutoriais proferidos por professores que atuam no exterior. Vamos começar hoje com o tutorial do professor Hirley Alves. Tá? Esse é um tutorial que é gravado, né? Então uma expectativa aí de 3 horas de duração. E ele vai falar um pouquinho sobre as ações que o Olo está tomando em relação às redes 6G. Podemos já então começar? Lembrando a todos, né, que tanto as apresentações quanto os tutoriais vão estar disponíveis no site do XG Mobile.
Olá, I am Hirley Alves. I am Associate Professor at University of Oulu on Machine Type Wireless Communications. And I'm also head of the Machine Type Wireless Communication Group and a leader of the Strategic Research Area 1, Team C, Massive Wireless Automation, that deals with IoT connectivity from theoretical, algorithmic, and some of the implementation aspects. So today I'm here for this tutorial on the evolution of machine type communications towards 6G. And I split the tutorial into 2 branches. So one focusing on distributed learning in M2C and the other one focusing on satellite IoT. So the idea here is that we explore these 2 different fronts, and which I consider them as promising for the next generation of wireless communications technologies. So I hope you like these tutorials. If you would like to have to keep in touch or would like further clarifications, please don't hesitate to contact me. If you have some interesting research ideas that you would like to discuss, you can find me at hirley.alves@olu.fi. And I'm looking forward for your feedback, and I hope you enjoy this tutorial video and this tutorial overall. So thank you, enjoy. In this part of the tutorial, we will focus on distributed learning in machine type communications. Before we go to technical details, I would like to thank my current and former students that you see here, and our collaborators. Without them, this research wouldn't be at this stage. And moving forward, what I would like to propose now is that we go over the motivation of why distributed learning is necessary in MTC, and then we can go go forward with this motivation and the contextualization and what are the tools that we will be using throughout this tutorial. So the massive machine type communication, MTC, is transforming the landscape of IoT applications. We are defining new standards for connectivity and communication across industries, from connected vehicles to smart agriculture to automated factories. MTC networks are now encompass billions of devices, constantly transforming data or transmitting data. And like traditional mobile networks designed primarily for human communication, massive MTC applications often require reliability, latency, and privacy measures while being able to serve thousands of devices. This transformation introduces unique challenges, especially for real-time communication, data privacy, and managing the communication overhead in dynamic resource-constrained environments. In response to these challenges, distributed learning emerged as a key approach to maintaining the effective and secure data processing within the MTC networks. Distributed learning addresses the core concerns of data privacy, latency, and scalability by allowing devices at the network edge to collaboratively train models without sharing raw data. Instead of centralizing all the data for model training, distributed learning models such as federated learning-based solutions enable devices to process and learn from data locally. This significantly reduces communication loads, as only model updates are transmitted or distilled knowledge go over the network instead of raw data. Among the most common distributed learning solutions, we have federated learning, which helps create decentralized, collaborative learning environments. In federated learning, devices independently train a local model using their data and share only the updates or changes in their models with a central server that is aggregating these updates to create a global model that will be then broadcast to the users. This approach maintains the privacy of sensitive data while reducing the need for high bandwidth data transfer. This is then an ideal method for applications such as autonomous driving, healthcare, personal IoT devices, where the privacy and autonomy of each device are critical. Another technique based on federated learning is called federated distillation, which optimizes this concept by compressing the learned knowledge into smaller, more efficient form, which reduces the data transfer further without sacrificing accuracy. By minimizing the amount of data exchanged, federated distillation is well suited to scenarios with limited communication resources. For example, rural IoT deployments, smart agriculture, where the bandwidth constraints can be severe. Added to those, we also have multi-age reinforcement learning, which is a promising approach for MTC networks that require real-time and adaptive decision-making across multiple devices. So multi-agent reinforcement learning enables multiple agents, for instance, autonomous vehicles or UAVs, drones, or sensors, to learn cooperative or competitive strategies based on shared environmental data and feedback. In MTC applications, multi-agent reinforcement learning is especially useful for optimizing resource allocation, managing interference, and coordinating tasks dynamically. Multi-agent reinforcement learning applications in MTC are vast, from spectrum management to coordinated sensing, making it a valuable tool for enabling intelligent, autonomous operations in complex environments. Despite these advancements, applying distributed learning models in MTC is challenging. One of the major issues is the variability of the data, quality and quantity across devices. Devices in different locations and applications may have vastly different types of data, which can lead to inconsistencies when training the models. Additionally, the dynamic nature of the wireless environment can cause significant variability in the network quality and as well its availability, affecting the model convergence and overall performance. Therefore, it is essential to design distributed models that can adapt to heterogeneous, large-scale, and ever-changing nature of MTC networks. Addressing these requirements call for robust, flexible learning models that operate efficiently across various devices and conditions, even with limited or intermittent connectivity. Effective solutions require careful considering of each device's resources, network conditions, and specific application needs. So there's quite a range of a wealth of parameters that need to be taken into account. So in this tutorial, we delved into these methodologies, examining how federated learning, federated distillation, split learning, transfer learning, meta-learning can be adapted to meet the needs of massive MTC applications. By addressing the distinct challenges posed by privacy, scalability, and resource constraint, distributed learning methodologies offer a promising path forward. They provide a robust foundation for MTC in the 6G era and set the stage for the next generation of IoT connectivity. And recently, this tutorial focuses on the results and outputs discussed in this recent magazine paper that we have called Distributed Learning Methodologies for Massive Machine Type Communications that is to appear in the IEEE magazine, IoT magazine. And this paper is also available on arXiv. You can have a look there as well, already now. So next step, we will discuss federated methodologies or federated solutions. Federated learning is a decentralized approach where devices train a shared model collaboratively, keeping data locally and only transmitting updates. This makes federated learning particularly valuable in MTC, where privacy concerns often prevent centralizing data. By exchanging only model updates, federated learning reduces communication load and enhances privacy, making it suitable for sensitive applications like healthcare and autonomous vehicles. So in a typical federated learning setup, as we can see in this figure, each device trains a local model based on its own data, which may vary widely in quality, amount, and structure from other devices. And periodically, each device sends its model updates to a central server, aggregating them to create an improved global model. We can see this here indicated by these arrows. So the devices, they compile their own models, and then as indicated by this blue arrow, it will send the updates to the base station, which in this case is doing the aggregation. And then once the base station collects the sufficient inputs from all of these different devices, it will compile or generate a new model, a global model that will be then broadcast to the devices as indicated in this yellowish arrow. So the base station aggregates the updates, updates the global model, and then share the model updates. This process allows the network to benefit from diverse data sources without requiring any device to share its original data, making federated learning an ideal solution for distributed MTC networks, where privacy and bandwidth efficiency are essential. And we say that because most of the MTC devices are considered to be IoT type devices. So they are usually limited in processing, and they are there to perform some specific tasks. So their capabilities are often reduced. In many cases, these devices are battery constrained, and in the future, it's envisioned that these devices may be even battery less. So the processing power that they have is very small in many scenarios, especially for monitoring and telemetry. So federated learning also reduces the need for these extensive data transmissions, which is beneficial for this type of resource-constrained or bandwidth-limited networks. This helps to improve the overall efficiency of the MTC system. And then this is primarily relevant as we want to reduce or increase the energy efficiency and reduce energy consumption of the devices, and also reduce the energy consumption of the aggregating models and machine learning models. However, implementing federated learning in MTC environments brings its own set of challenges. One of the key obstacles in this front is heterogeneity of devices. Devices vary widely in processing power, network reliability, and energy capacity. This means that these devices have constraints, or they're limited in terms of their processing power, the ability of handle learning models, and even in some cases the communication models. They have very simple communication protocols or communication radio access interface. The network reliability varies. These devices are not always active. They may wake up to respond to some sensing trigger, to some functionality that is pre-programmed. So they are not always connected, and then establishing the connection and then sending these updates generates lots of issues when we're doing the aggregation. And as commented before, the battery limitations. They are often battery constrained, so they're processing uh, activities that consume lots of energy might not be uh, desired in the long term of the network for the longevity of the network. So in an MTC network, devices vary significantly. Some may have some ample processing power and reliable connectivity, while others may be battery powered or low cost sensors with limited resources. And then these are the cases where we can consider an IoT devices as an autonomous driving vehicle, and it's processing some functions that portion of that autonomous vehicle is one IoT device or has functions of IoT device. Or in a cyber physical system, sensors measuring some processes, for instance, energy consumption of a household, the smart meters might be seen as energy IoT devices, and then they may have but may not be constrained in terms of energy, but they might be constrained in reliability because they might be operating under a LoRaWAN type of radio access technology. So the updates that can be sent are very small and need to be compressed because the payload that network allows to be transmitted is very small compared to a cellular-based solution as NB-IoT or 5G NR MTC or 5G NR RedCap. So this diversity complicates the synchronization of model updates, and not all devices can train communicating at the same pace. So this leads to several variations and heterogeneity in the network. To address this, a variation known as asynchronous federated learning allows devices to send updates independently without waiting for all the devices to complete their training. So that would be one alternative solution. And asynchronous federated learning improves the efficiency of the learning process by allowing devices to participate based on their capabilities. Still, it may also introduce some inconsistencies in the model due to non-uniform updates. So this happens because we're now trying to tailor the network to the devices and do a device-centric type of updates and personalizing the network. So this also leads to several challenges because now we need to know more about the devices that are in the network and how to collect that information and tailor then the updates based on these. So it also increases the computational complexity at the aggregator phase or on the aggregator side. Another significant challenging federated learning is the communication overhead. Since federated learning relies on regular communication between devices and the central server or aggregator, it can load on network resources heavily. And this is particularly problematic in dense MTC networks with limited bandwidth or devices in remote areas. There are several techniques that were developed to mitigate this issue, aiming to reduce the size and or frequency of the updates sent to the server, allowing for more efficient communication without sacrificing the model accuracy. For instance, we have update sparsification, which refers to sending only the most significant updates, for instance, only if there is actual changes in the model parameters, and ignoring or delaying transmissions of less critical updates. Two popular model compression techniques are quantization. So this involves reducing the precision of the model parameters or updates. For instance, representing them with fewer bits. We can take the representation from 32-bit floating point to 8-bit integers. So we're basically truncating the the values of the model or the weights of the model. And then we can also do pruning, which involves removing the unnecessary or less important parameters or weights from the model to reduce its size and complexity. So in this case, we could judge what would be the most significant updates and zero out the other weights in the model so that you don't only need to transmit uh, a simple encoding with the highest with the weights of the most important updates. This simplifies the transmission and reduces the overall complexity. However, it may come with some limitations and reduced accuracy. So this technique can further reduce the update size, ensuring that devices with limited bandwidth can still participate in the learning process. Here we have one example of these cases. So let's look at this example highlighting the trade-offs between centralized and federated learning in a massive machine-type communication scenario. So we have here one base station placed at the center of a network and several devices spread around this base station. And then in the centralized case, the devices train a neural network based on the MNIST dataset for image classification with configurations comparing centralized and then the federated learning. Under different conditions here, we have fewer or users in the MTC case, so 10 or 100 devices. And in the centralized case, all the devices send their raw data to the central server and do the aggregation and the model training. While in the federated learning case, devices train locally and send only model weights to the server for aggregation. And in this case, we also allowing the devices to compress the data. So we're taking the 32-bit representation and compressing to 4 bits, and then also to 8 bits. And that is illustrated. The 4-bit compression is the orange curve, as you can see here. So by doing a very heavy compression, we have very poor accuracy because we are um, doing a quite gross approximation of the weights. So this is reflected then in the accuracy performance. So it barely converges, and the accuracy is very poor compared to the other methods, to the centralized case that is shown in blue here on top, and to a lighter compression, as let's say, is still quite large, but much lighter than 4 bits. So this 8-bit compression, so approximating float integers to integer, float 32-bit floats to 8-bit integers. It's much better in terms of convergency, as we can see here, and also in terms of accuracy. There's a very small loss compared to the centralized case, which has the raw data instead of only the model updates. The other case here that we have is the dense federated learning with 8-bit compression, and then the difference between the yellow and the purple here are that we have densification in the network, so we have more devices. So these results illustrate the important insights. First, federated learning with 8-bit quantization closely matches the accuracy of decentralized learning with a few iterations. So we can see here already for less than 10 iterations, we already have very close performance. However, when the network scales, in this case, the purple curve, to 100 devices, federated learning experiences lower convergence and reduced accuracy due to increased synchronization demand across devices. So that's why we see a very large gap here at the beginning is lower convergence here. So from a few iterations to close to 30 iterations, so to ensure convergence. And then the quantization also impacts the performance. While 4-bit quantizations halves the communication overhead, it also halves pretty much the performance. So we drop from 90 something percent to close to 60% accuracy, especially if we compare to 8-bit quantization. So the communication overhead is a key factor here. So over 100 iterations. So if we take the network once we are at this stage here, the models have converged. Federated learning require 5 times less communication than decentralized learning. So make it much more bandwidth efficient. This efficiency is critical especially in massive MTC networks with limited transmission capacity and battery constraints. So where transmitting large data sets like centralized learning could drain the resources very quickly. However, federated learning has its challenges. dense networks can face delays and reduced accuracy, and due to constrained resources and also synchronization issues. To address these limitations, alternative distributed methods such as federated distillation, split learning, and meta-learning can complement federated learning and improve performance of, particularly in case of resource-constrained MTC networks. So on that note, we now can take a look what is federated distillation. So it is an adaptation designed to optimize the communication and resource use. Federated distillation enables each device to train a model on its local data and then distill, here is the main difference, the learned knowledge into a compact, summarized form before sharing it with the server. So this distilled knowledge, often represented as a set of probabilities or a softened version of the model output, some inconsistencies in the model, transferring large model weights. We can look into this figure, as we have here an example. We have a few devices that are doing the local training, and then the server is aggregating the information in the center. So let's take a look at what this means. And one thing, these logits that are being transmitted are the unnormalized scores of the model. So either a soft output or a probability distribution or a set of probabilities over that for that model. So let's explore the federated isolation. It's in this variation. In this particular example, we have partitioned it into two distinct classes. They are represented as blue or red, and each device performs classification locally and generates probabilistic soft outputs. They are called logits, as you can see here in blue. The uploads of these logits. They contain information relevant to all classes. Instead of transmitting the full model updates, the device sends their logits to the server, as we can see here in blue. The server then averages these logits and then broadcasts them back to all the devices. Each device then uses the information relevant to its specific class and aligning with the current training sample it's working on. So it takes back here in orange this average output broadcast and then inputs this in its own model and then updates based on its needs. So every one of them will send information about the two classes, the blue and the red, and they have all different needs. And once they have the aggregated model, then they can apply this updated or updated model or simplified model on their computations so that it improves their performance and can expedite convergence and improve overall performance in terms of accuracy without need to transmitting the whole data or the whole model to the aggregator, as in the federated learning case. This approach significantly reduces the communication overhead because the logits are much smaller than the full weights or the whole set of parameters, and transmitting only logits resulted in this previous example that we saw in more than 100 times less communication than traditional federated learning. So this reduction could also shorten iteration delays as smaller data sizes make it possible to send updates in a single transmission rather than across multiple rounds. So as we can see here, we have, by doing this relatively simple procedure, we can reduce the communication more than 100 times compared to this previous example where we have the federated learning and the centralized learning. However, as usual, there is a trade-off. While federated distillation is highly efficient, exchanging minimal information can impact accuracy, so devices may require longer training periods to achieve acceptable performance. However, despite this, federated distillation offers a compelling solution for scenarios where communication efficiency is critical, particularly in the case of bandwidth-constrained networks. For example, as in factory automation or smart agriculture, where devices have limited computational or communication resources. By minimizing the data exchange between devices and the server, federated distillation also helps to reduce the communication costs, which enables federated learning methodologies to be applied to scenarios with strict bandwidth. Federated learning methodologies offer substantial benefits for MTC applications, providing a pathway to achieving scalability, privacy, and efficiency across many connected devices. However, as we can see here, one of the main limitations identified already in the literature is with federated learning and federated-based solutions is once the communication is taking place, that each device will then communicate to the server and send its updates, and then the base station may request or the devices may send directly the updates to the server, but one at a time. So in a cellular system, we could say that this is a TDMA-like system, so a time division multiple access. So once this device terminates its broadcast of the updates, then this one will start and so on. However, this can be very slow process as we have very large networks. This can be improved over no multiple access solutions and so on, but still that is one of the key limitations, and then determining the number of devices to do the aggregation first, and then updating the model and transmitting the updates. So this can be very time consuming and increase the delay in the network, especially for the users from the UE side. So this device here would need to wait for the whole round of updates until the server sends a new model, a version of the model. So this may be quite time inefficient, so generating a lot of latency. One way to overcome this is called over-the-air aggregation or over-the-air computing. So in this case here, it's a method that enhances the communication efficiency and reduces delays in federated learning, because over-the-air aggregation uses analog computation, where the base station is aggregating non-orthogonal updates from the devices and broadcasting them with a single resource block. What does that mean? So if you take this figure here on the top, each of these devices, instead of sending on each time slot or each frequency slot, whatever the underlining resource block management here is, they will all be sending at the same time. What they do is based on path loss and channel inversion, for instance, they can quantify scale their transmission, so that the base station is perceiving perceives the signal uh, efficiently and is able to recover that signal. So these devices that might be, in this case here, this device seems to be further away, so his wave form is much more attenuated than the others, which may mean that he has a further distance from the base station or a severe path loss. So in this case here, he would be able to invert the path loss, apply invert the path loss and transmit with that power. So he would be using, he has a good channel condition, so he's using low channel power, sorry, and then his waveform is attenuated compared to the second guy that might be farther away, so he's using a little bit more power. So if we look at only at the amplitudes here, and then this might have a very weak signal, so he needs to amplify quite a bit. And then all of these will be transmitted and be perceived as a single waveform at the base station. So each one of them is sending their own weights updates, and then the base station is performing non-orthogonal multiple access and aggregating this over the air. So what's the main advantage of this? Well, we just eliminate n round of data collection, so by doing that in only one round. The limitation here is that we then need to do efficient recovery of this signal, of the aggregated signal at the base station, but we already have efficient solutions to handle this in the literature, and that because we basically have a MAC channel here. So despite its efficiencies, over-the-air aggregations face noise, data heterogeneity, and synchronization issues. So careful power control is essential to maintain the balanced updates and avoid aggregation errors. That then these aggregations can be propagated through the model and then generate slow convergence and even render the model completely inefficient. To tackle this, a scalable over-the-air aggregation systems like random access based over-the-air federated learning have been proposed. The systems address issues such as unknown channel state information and efficiently encode gradients or the weights using randomized vector quantization. So in this paper here we have done uh, something similar to this approach, and what we introduced is in a single cell type of system, we have one base station collecting the updates of several users, and then that would be the conventional methods. What we have done in this particular paper is that we have distributed the base station and leveraged centralized uh, distributed massive MIMO. So each of these access points has a several number of antennas and is able to connect to several devices. And then once they collect this, all of their inputs is processed over a central common aggregator or over a CPU, and then this information is then propagated back to the devices here that are in the network. So if we had, in the previous cases, we had one base station, several users, we were collecting information from them. In here's we have several base stations doing the same steps. We have one main difference now, that is the processing is done at a CPU or at the core of the network, and then this is propagated to every single one of the base stations. We also have a different means of aggregation here because the path loss perceived for each base station might be different, but the underlying idea is the same. So in this particular case, we are comparing massive MIMO with centralized massive MIMO and distributed massive MIMO, applying then over-the-air federated learning. Our results here, as we can see in these two figures, they show that distributed MIMO achieves superior performance. We are able to reduce the average transmit power by 31% and the aggregation minimum square error by 16%. In scenarios with 200 devices and 4 access points, as we can see in this figure. So we have a quite large number of quite great reduction in terms of power consumption. The main idea here is because since we have more APs available, the path loss distances to do this conditioning of the to do the channel inversion is much more favorable to the devices. So shorter distance, better channel quality for the devices, better use of the available energy. And that's what is reflected in this result here. In here we are basically seeing MSE of the aggregation, so how good is our aggregation, and also seeing the convergence. So here we have the centralized case as in the previous scenarios, the distributed case, and then here is a comparative work that uses a similar approach for centralized massive MIMO with over-the-air aggregation. One of the main highlights is that this type of distributed architecture improves the accuracy and conserves energy. So we can have some benefits, especially for the users in terms of energy preservation, making it highly suitable for resource-constrained MTC networks. So overall, over-the-air aggregation is a promising research area for the next generation of wireless communication systems, and has been gaining quite a lot of attention in these previous years. So despite these variations, there are still many challenges, especially concerning data heterogeneity in MTC networks. This is particularly relevant for MTC networks because devices generate data in diverse formats, distributions, and quantities, and also the devices have different uh, operation modes. So they might be uh, full-time on transmitting regularly, periodically, or just might be transmitting events or doing or performing under wake up calls and having deep sleep modes. So this generates a very different types of traffic profiles that is very irregular compared to human type based communication, where these type of models were initially developed for. And so that's why heterogeneity of data is one of the major issues for MTC type communication. For instance, in a smart healthcare network, data collected by a wearable health monitor may differ significantly from the data generated by an environmental sensors regarding, for instance, temperature or other environmental parameters, CO2 or humidity. And this variability and relevance of this data is also quite distinct for this particular example. This heterogeneity can lead to a problem known as non-independent and identically distributed non-IID data, where the local data sets across devices differ in ways that affect model training and conversions. So this non-IID data can slow the learning process or result in a poorly performing model across network. To address this, researchers are exploring personalized federated learning approaches, and then these alternatives adapt the global model to each device's local data, allowing better performance even with varied data distributions. So, but this also comes with um, one constraint that we also need better or increasing the complexity in the data aggregation phase and tailoring the the federation or the aggregation to the devices. So that is a trade-off. You improve performance, but you also increase the complexity across the network. Another point is that by integrating federated learning in its variants, massive MTC networks can achieve greater efficiency. So we're seeing a few examples where this can be achieved. So in terms of efficiency, we can improve accuracy and convergency. We also shown in these cases, particular cases here, that the privacy is preserved. So we haven't shown particular metrics to quantify privacy, but we've shown that the data or the raw data is not broadcast for aggregation. So we don't need to collect that data. That amount of data doesn't need to be transmitted from device to aggregator. And also enables scalability. We see that we have some losses in terms of um, synchronization, as we saw. If we go from 10 users to 100 users, we had a small decrease in performance, but we have gained significantly in terms of number of users in the network, and then this can scale even further. And then with, for instance, mechanisms such as over-the-air aggregation, we can have even more users over the net in the network, because then we reduce the amount of latency that is required, and then we can improve and make the aggregation more effective. Overall, this creates a flexible foundation for applications in diverse, large-scale, and resource-constrained environments. While challenges such as communication overhead, device heterogeneity, and data variability remain, federated methodologies continue to evolve. And with its advances in asynchronous or personalized learning, model compression approaches, this brings us together to fully realize the potential of these solutions, especially distributed learning MTC. What we will see next is a few other techniques that can be associated with federated learning that can improve even further and address some of these challenges that we discussed so far. So next we will be seeing split, transfer, and meta-learning. So let's take a look first in split learning. As MTC applications become more complex, methods such as split learning, transfer learning, and meta-learning have become essential for optimizing the resources and addressing the scalability in distributed settings. These approaches provide solutions that allow learning models to operate in diverse environments with varying data distributions, computation capabilities, network conditions, which are the typical challenges that we just covered. By tailoring the learning strategies to match device capabilities and contextual needs, these methodologies ensure that MTC systems can remain efficient, adaptable, and responsive to real-time changes. And this is very, very important as we more and more need fast response from not only collecting data passively and then updating the models, but we are actively engaging with these IoT type devices or MTC type networks that are in the environment, and the ability for them to be responsive to real-time changes is very important. So first we will take a look at split learning. We have here in this figure a model on how split learning can be represented. So the input layer on the device side in the bottom, and then on the top side we have the output layer that is on the server side, and throughout we have backpropagation. You will see here in a line in red in the middle, and that is where we are doing the split learning, where we are splitting the layers, and that's where the name comes from. So split learning is a distributed learning approach that partitions a model so that a training occurs in segments across multiple devices or between devices and the cloud. This approach is particularly beneficial for MTC, especially for limited computed resources. So it may be unable to handle the full computational load of training or complete model. For instance, consider an IoT-based health monitoring network in which we have one wearable device to track patient data. These wearables have limited processing power and the battery life, so making training a complex model directly on the device. So that becomes quite impractical. So with split learning, the wearable can handle only the initial model layers. So we would be providing the model on the device side only with the input layer, so the data, and a few of the layers of the, for instance, a convolutional neural network. So we would take the first, the second, maybe the third layer, and then have the cut here at this point. So here would be the splitting, and then the rest of the processing would be done at the server side. So therefore, the bulk of the training can occur on an edge server or a cloud platform with more powerful computational resources. So split learning reduces the computational burden on the MTC device and enhances privacy and as well security by keeping sensitive data local. Only intermediate activations from the model are sent to the server for further processing. So this also minimizes the amount of potentially sensitive data transmitted over the network. Overall, this approach is well suited to applications where data privacy is a priority because you're not sharing the raw data and you are sharing already pre-processed data. And this is particularly important in health monitoring or smart home security, for instance. And is quite relevant for many other applications under the MTC domain. Despite its advantages, split learning faces a few challenges in terms of latency and synchronization. So each time the data is passed between the devices and servers, there is a delay affecting the real-time applications. So whenever I am defining the cut here and how deep this cut or this split layer happens, I need them to communicate to the server side and propagate and then send this information to the server. Once this is then further processed on the server side, we also need to send back the information so the device is able to recover um, the output of this model or take the actions that are needed. So then there is quite have an increase in overhead in terms of the communication side. Another challenging condition under split learning is that the devices require some coordination across the devices, especially where I have several devices. Or aggregating over, for instance, a federated learning network where I would collect the information from several devices with different split layers. So this can be complex in highly dynamic environments with varying network conditions. As you can imagine, as I already need to communicate a little more to coordinate these actions or coordinate the layers, if this needs to be done in a highly dynamic environment, I would require even more communication exchange, and this becomes even more challenging as the network conditions change. So these are challenges now that we have with split learning and the optimization of split learning over federated networks in MTC settings. Another technique that is quite relevant in this context is transfer learning. So here again we have a similar uh, structure. As we can see here, we have one device, its own data set, and then its model. And then we have another device, its own data set, and then its own model. And we have two distinct tasks. The main point of transfer learning is that one device may be performing one task and has some information about this task. And if we find that there is some similarity between task 1 and task 2 over different devices, we can transfer some of this information that was already established here in the first case to the second one. So transfer learning is another approach that offers substantial benefits in MTC, particularly when the label data is limited or when devices are deployed in different but related environments. So you can imagine that if you had one device in a smart factory setting performing some communication in one ambient, if we place another device in the same environment in different position, it would be able to use some of the statistics or some of the knowledge that this model has about CSI and other environmental parameters, for instance, for that device in order to expedite the training for the second device. So this would be helping the device to quickly get on its feet and doing its tasks. So transfer learning leverages the knowledge from the model trained on a source task, so one primary task. It applies it to a new yet related target task. So the tasks in this case here cannot be very different. They need to be somewhat related. So this can be particularly useful for MTC scenarios and applications like network optimization, where conditions vary across locations. For example, a model trained to optimize coverage and bandwidth allocation in urban areas can be adapted to rural areas with minimal retraining, saving time and computational resources. This flexibility enables MTC systems to adapt to environments quickly, making transfer learning a valuable tool for large-scale deployment across diverse geographic areas or types of infrastructure. Another example that we can use transfer learning is for localization. If you have a network deployed in one floor of a building, you could use transfer learning to devices that are on the other floors of the building. So learning the localization or estimating the position of the devices based on communication signals using transfer learning, the next devices that join the network on different floors could learn based uh, on information available from the devices that arrived first on different floor. So this expedites the deployment and facilitates the training of new devices. So reduces the training overhead. Transfer learning is also valuable for applications where data collection is costly or especially time consuming. So in cases like predictive maintenance for industrial IoT, where sensors collect data on equipment health, collecting labeled failure data can be challenging. By pre-training a model on generic machine health data, then learning allows the model to adapt quickly to the specific characteristics of each device, making accurate predictions with fewer labeled points. So this is in this particular example here, failures on equipments are quite rare. So it's really hard to identify them and then to have these data sets with this rare data. So if we have a generic data set with some examples, it would expedite the training for and the amount of training that is required for the network, which will be much smaller. However, transfer learning faces challenges as well as any other methodology. When there is a significant discrepancy between source and target tasks or the data distributions, the problem known as negative transfer. Oh, no, it creates a problem known as negative transfer. In these cases, the model may perform worse on the target tasks due to transfer of irrelevant features. Addressing this issue is one of requires careful selecting of source models or finite tuning strategies to ensure that transferred knowledge remains beneficial. So this is one key limitation. So if the tasks here are very different, these may generate this negative transfer, which means that whatever was trained here was trying to be used in this second task. They are completely they have no similarities. So in this particular case, the performance or even the convergence of the model might not converge, which may lead to further delays and necessity for retraining. So we need to be very careful when selecting the tasks and how they are related. So there is quite a lot of work to be done so that we can employ this solution. So there's a lot of fine tuning in this in selecting the source models and fine tuning these strategies. The last solution that we'll be discussing for this part is meta-learning. So meta-learning is often referred as learning to learn. It is in this model here, we also have in the last image what we are called meta-train and meta-test. So we expose several devices, 1 to n devices, to a series of tasks. And we have a support set and a query set where these devices can then try to learn their own parameters. And then we have a model that oversees this process, and then we'll be then trying to acquire some information that can be applied to any other model later on, so that this process can be repeated without doing the training for the individual users. So whenever I have a new user in the system, I will provide him with this common parameter set and common parameters. So this is the indicating what would be the 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 model indicates what is the optimal parameters or the suitable parameters here, and then the device, based on its own data, will then fine tune these parameters to its own model. What is the main advantage here is that we can have a very much faster training overall or network optimization of the network or of the model. So meta learning is quite relevant, especially to reduce the training or the need of training data. So meta learning, often referred as learning to learn, is designed to equip models with the ability to quickly adapt to new tasks or environments with minimal additional training. This adaptability is essential in MDC, where the network conditions, device capabilities, and task requirements can change rapidly. In a meta-learning framework, the model learns a generalizable strategy to fine-tune quickly the various tasks. So that would be what we call usually as common parameters. One popular meta-learning method is called model-agnostic meta-learning, MAML, which trains a model to perform well on multiple functions and promptly adapts to any new similar task with a small amount of data. In the context of MTC, meta-learning is valuable for scenarios where devices operate in dynamic environments. Industrial IoT settings, for instance, or autonomous vehicles networks, UAV networks. For example, an intelligent manufacturing environment, machines may need to adjust production parameters in response to real-time feedback from sensors to the production line. A meta-learned model can quickly adapt to the specific parameters of each new product line or operational condition, improving efficiency and reducing downtime. Similarly, meta-learning allows each vehicle to rapidly adapt to its model based on local driving conditions in a fleet of autonomous cars, for instance, enhancing the safety and efficiency. Another example that we have done of last year was applying meta-learning to reduce the amount of pilot training. So we had a network where we had several devices, and then those devices were able to communicate in an orthogonal multiple access way. So using NOMA. So each of these devices would communicate to a base station on the uplink, transmit pilot symbols, and what we want to do then their tasks or their support and query set, what they were doing here, if we translate to this example. So the device 1 to device N would send pilots to the base station to acquire the channel state information. And then the base station was learning this, the channel of these devices. They would be in the same environment, but with similar channel conditions. And then we were learning the parameters of this overall setting. What we want then is to introduce a new device that would come and do the channel measurements as well. So we would train sending pilots, but the idea here is that we would be able then to reduce the amount of training. And what we did here, we would be collecting these pilot sequences, and up to the point that we had sufficient statistics of the channel. So we were satisfied with the quality of the estimate of the channel. So for these cases of 1 to n devices here that were the first ones to communicate, we have a few tens of pilot symbols sent to do this channel estimation, and as well as compared to conventional MMSC estimation, and we would need a few tens of pilot symbols to do the channel estimation. By doing this process with meta-learning, we can reduce from tens of symbols to 1 to 2 symbols at a transmission. So we have at least a tenfold reduction in the number of pilot symbols. This is very relevant, especially for massive MTC setups and ultra-reliable communication networks, where I need a very fast communication. And then being able to send 1 or 2 pilot symbols, estimate the channel, and having the message reliably delivered is very important. What we did on top of that is to allow the devices to transmit with overlapping transmissions. So these two devices here would be sending their own pilot sequences, but they would see interference from each other, and then this other new device, would also be seeing interference. So in a non-orthogonal fashion. And the base station is then able to extract these 3 different users with a very limited number of pilots again. And then in this particular case, again, when we use NOMA, we were able to reduce the pilot estimation from a few tens of pilot symbols to 2 to 4 pilot symbols, depending on the target performance. So that is one way to use meta-learning for a more physical layer-based type of example. So this is a quite promising technique for MTC, and is quite relevant in this case. Meta-learning has several distinct advantages for MTC applications, where there is a need for quick adaptation and customization across devices for different tasks. However, it also comes with several challenges, particularly regarding computational overhead. Meta-learning requires the model to train on multiple tasks to learn the generalizable strategy, which can be resource intensive. In MTC networks where the device have limited processing power, it may be necessary to offload the initial meta-training to a central server or to the edge computing node, or to offload all the heavy complex tasks to the base station, so the users would be benefiting from model outputs. But once the meta-learn model is deployed, each device can perform rapid local fine-tuning with minimal computational burden, making this approach feasible for resource-constrained environments. So this would be very beneficial. Together, split transfer and meta-learning methodologies provide MTC networks with the tools um, with the tools needed to address the unique challenges of distributed learning. Split learning optimizes computational efficiency and data privacy by dividing the model between devices and cloud, making ideal for applications where privacy and resource constraints are vital concerns. Transfer learning, on the other hand, enables the reuse of knowledge across different yet related tasks. Very important this point, that the tasks need to be related, enhancing the adaptability and reducing training time for new deployments. And then meta-learning equips models with the ability to quickly learn and adapt to a wide range of tasks, providing the flexibility needed for real-time applications in dynamic and unpredictable environments. So these 3 solutions, they complement each other, and then they complement also the federated approaches. So their combination become quite powerful, and then the combination of these different tools is what is now being explored as future directions in 6G. So each of these methodologies contributes to a scalable yet flexible framework for MTC, enabling models to optimize learning based on the specific device capabilities and contextual requirements. As MTC networks expand, these approaches will play a critical role in enhancing efficiency, privacy, and adaptability. This will then ensure that MTC applications meet the rigorous demands of future IoT systems and 6G networks. These advanced learning methods allow MTC systems to maximize resource use, optimize privacy and security, and adapt to the network environment. Split learning, transfer learning, and meta learning form the backbone of intelligent distributed MTC network, capable of addressing the challenges of the future networks. We have one more type of methodology that we want to discuss here, and that is called multi-agent reinforcement learning. And I would like to give you a brief introduction about reinforcement learning so that we can be on the same page, and then go to the multi-agent case, and also to some new quite recent variations of this type of models. So reinforcement learning, or RL, is a decision-making algorithm and a critical branch of artificial intelligence. It enables an agent to learn optimal actions by interacting with its environment. Reinforcement learning environments are typically modeled as Markov decision processes, or MDPs. So we have here in this figure an example. So figure A that we have here on the left shows that the agent observes its states. So the agent here being this robot, it observes some states and then interacts with the environment, here the world. Takes an action and receives feedback as a reward. So it sees some state, he is in a position, it will take an action and then will receive some reward. So it will that will indicate the quality of its interaction with this environment. A high reward is given if the action benefits the agent. A low reward or a penalty is applied if it does not. The agent's ultimate goal is to maximize its cumulative reward. It's important to emphasize here that we want to maximize the cumulative reward. And that is done by discovering the optimal policy. So that is, what is the optimal policy? The optimal policy is the strategy that guides this agent to make the best decision over time. So we are at this instance, this agent will go and takes a policy, it will act and over the environment receive the reward update, and then this experience is passed for the next policy, and then it takes a new policy again and keeps interacting this. And over time, it wants to maximize its define the optimal policy and maximize its cumulative reward. So bad decisions are the agent's decisions, and then based on the reward, the agent can fine-tune its decision process here, so that to avoid the decisions that give him a bad type of reward. While effective, this traditional method here, that is called online reinforcement learning, is struggle with the high dimensional environments. So as you can imagine, when we have a large number of parameters in a large and complex environments, the state action is become very high dimensional. So these become the available policies and decision over these states becomes very complex. and then this complexity of these models grows exponentially, or polynomially. So this is where then deep reinforcement learning comes in. So deep reinforcement learning combines reinforcement learning with deep neural networks. And then in this particular case, these deep neural networks act as function approximators to estimate the Q function more effectively. So the idea here, when we have deep reinforcement learning, we have accumulating this experience. So in the particular case of reinforcement learning, traditional reinforcement learning, we accumulate the experience, we define our Q function, which is, or one of the options is to define this Q function that is your estimate of uh, uh, Q function is a proxy for the experience that the agent experiences over this environment. And then what this neural network does is, now I am learning about this environment. I am taking this knowledge that I'm getting from here, and then the rewards. I will uh, store this information in a buffer, so the experiences are stored. And then what I do here to estimate the Q function, as it becomes very complex and highly dimensional, I am taking this neural network to approximate the state action. So I am trying to reduce the complexity here in the estimating by offloading this process to a neural network. And then I will do again this new policy, store new information, and then do the training again and estimate and so on. So I am able to do uh, my tasks efficiently. So that is what we are trying to illustrate in figure B, that the current state is fed into the neural network, which outputs the best action. The neural network is trained to predict the optimal Q function by iteratively adjusting its weights. One of the most powerful deep reinforcement learning algorithms is the deep Q network, known as DQN, which means that which has been shown to solve large dimensional environments in just a few interactions. So it becomes quite effective to introduce this neural network here, because we then are able to resolve this Q function quite fast, or with guaranteed with high convergence. Deep neural networks operate as an off-policy reinforcement learning algorithm. So unlike traditional on-policy methods, deep Q networks learn from the past experiences stored on a replay memory buffer. So that is the buffer, and that's why it's off policy. So we're taking the experiences that are stored in the past to inform this neural network. And instead of relying only on the real-time interaction with the environment, as in this case here. So we don't have a buffer here, so we take the state, interact with the environment on real time, and then move forward and do the decision. In this case, we are storing information on a buffer. So this ability to learn from these diverse past policies allows the DeepQ network to update the current policy more efficiently. It makes it particularly effective in complex and high-dimensional environments. Now, you can imagine that this is for one agent. Now, if I have several agents, it would be a similar process, but instead of having one agent here with one policy and one state action, I would have the same environment but several agents interacting with that environment. And then these actions may interfere with the other actions of the other agents. and then that is then reflected in the policy, and then for the particular case of deep neural networks, capture deep reinforcement learning capture in the buffer, in the memory buffer, and then the policies also reflect the actions of the other agents. So in multi-agent reinforcement learning is an extension of traditional reinforcement learning applied to environments with multiple autonomous agents, and the emphasis here on the autonomous agents. Each make independent decisions while interacting with other agents. In multi-agent reinforcement learning, each agent would be reinforcement adopt mixed strategies, aiming for their individual gains or a collective outcome. Therefore, this makes multi-agent reinforcement learning ideal for distributed MDC systems where multiple devices must operate autonomously, but coordinate actions for effective resource usage. As you can imagine, one of the applications of multiple agent reinforcement learning would be to rate resource management, where the actions of the users may interfere with the others, and then generate an interference map across these different users if all the users decide to communicate at once. So by allowing the agents to cooperate, they can come up with efficient radio resource mapping that would enable a better performance overall over the time. So, agent reinforcement learning is available for distributed systems such as in MTC, where these devices, or in this case agents, operate autonomously and coordinate their actions to optimize resources across network. This brings and their cooperation or competition can lead to better performances and definitions of better policies. So its decentralized approach empowers each agent to make independent decisions while considering others, enabling efficient use of shared resources. For example, in a UAV swarm for smart agriculture, for instance, each UAV acts as an independent agent that learns to coordinate with the others to cover large areas efficiently, avoiding overlap coverage. Through reinforcement learning, each UAV can learn optimal flight paths to minimize the energy consumption and improve overall crop monitoring efficiency. And if we're thinking on communication perspective, we can improve the communication capabilities and the ability or minimize age of information, optimize access to the network and scheduling and resource management of these devices, given these different UAV swarms that given each individual UAV in this UAV swarm. In MTC, multi-agent reinforcement learning is especially valuable for optimized network resources and managing interference in dense device deployments. So, for instance, in a cooperative scenario, dynamic spectrum allocation agents may work cooperatively to maximize the collective reward. Devices must learn to avoid interference and share the bandwidth. In a competitive case, devices compete for limited resources like bandwidth or power. And then this versatility that makes multi-agent reinforcement learning a robust solution for applications with adaptive resource management. We have here one example, for instance, in table 1. And in this particular case here, we have exactly this UAV setup where we have UAVs operating in a swarm setting. So we have several UAVs, we have several devices, UEs, on the ground, and we even have blocked areas or restricted areas. So, for instance, a zone where this UAV cannot pass or cannot fly by, a restricted zone, or a building that is forbidden to fly over or fly around. So the UAV needs to determine the path to be able to collect information from these different devices without entering this blocked area. So the idea here is that we have this UAV swarm. They are collecting the data for these different clusters, that as we can see here. We clusterized these users. They are in different geographic areas, and we have several UAVs. They are initially located at the beginning of the corners of the network. And then they collect information here and relay or offload to this base station in the center. And in here, in this table, we have several multi-agent reinforcement learning algorithms doing cooperation, competition, and then we examine how much signaling is required, how much information they are exchanging, how much space spatial computation is required, so that means space complexity. So how in terms of dimensions, how high is the number of dimensions that is required for this type of model? What is the time computation or time complexity for this, and the overall performance. So this table 1 compares these different multi-agent reinforcement learning schemes, considering the message exchanges that what we're calling signaling the number of computations performed, what we are calling here space complexity, the test time of the algorithm, so which is the time complexity, and the convergence to an optimal policy. So that is the last here, which is the performance. The most straightforward approach is independent multi-agent reinforcement learning, which is this first one here on top, where each agent solves its own single reinforcement learning algorithm that is a deep Q neural network, and it doesn't consider other agents in the environment. So it does its own thing, it doesn't cooperate, it doesn't care about the others, even if they cause interference. So as we can imagine, there is little computation complexity, little time to compute, low signal because the signaling there is not much exchange of information between these users, and it's very low performance as well. And we can see this also here. In terms of average AOI, these green bars here. In this particular case, where we have a larger number of users, this becomes much worse than the other methods, even compared to common random walk if I just let these UAVs walk around randomly, following a given distribution. That is because there is no exchange of information between these agents, so it might be the case that they are all looking into the same region here and stuck to this region and never collecting information from these other devices, which will be the case that the average AOI will be very large. And that is what is reflected here with the number of clusters going very high. So the main limitation is that then in this case, this mood mood agent reinforcement learning, the first algorithm here, has low computation overhead, low number of computations, and low latency. However, it could perform better in hard-dimensional state action spaces, such as for resource scheduling problems, where the interaction between these devices might not be as relevant. However, as the number of devices in the network which would require this agents to communicate a little bit more, to exchange information, for instance, on which areas they are coming from, for instance, this lack of information limits its performance, as you can see here. We have then partially collaborative multi-agent reinforcement learning. So this PC O here, this is the second one. So in this case, the agents partially share information with other agents. The shared information can be the agent's rewards, the states, or the actions, and it has relatively low signaling, low computations performance, and high latency. So there is the impact of effect of exchanging information across these different devices. On the other hand, we have collaborative MAR, or collaborative multi-agent reinforcement learning, that is the next one here. We had then we allow them to fully share all the information, states, actions, rewards, everything. And then in this case, the signaling is very high, so they are exchanging a lot of information. The computation becomes very high. The time complexity becomes very high because it takes a longer for this information to be shared, and then also this information to be passed to the model and to convergence, but the performance is high. One advantage of this is that since everything is shared, it guarantees convergences to the optimal policy because the agents are serially sharing their information to one another. However, it has lots of limitations in terms of the signaling, the complexity and conversion. And the last one, the C reinforcement learning, is the case where a multi-agent reinforcement learning is converted to a single agent problem, which we're calling here centralized reinforcement learning. In this case, each agent transmits its state spaces to a central unit that merges the received spaces from each agent. Then it computes a reinforcement learning algorithm that optimizes one action vector for all agents and relays it optimal actions for each agent. So in this last case here, we are collecting information from every single agent, calculating it as if it were a centralized reinforcement learning or as a single agent, and then broadcasting again to the other agents so that they can update their models and take the actions. This reduces significantly the signaling overhead. However, one of the main limitations here, since we are collecting information of all of these different agencies, is that the space complexities and the time complexity are very high, even larger than the fully cooperative multi-agent reinforcement learning. Which is a limitation because this method, centralized reinforcement learning here, CRL, that we are calling the last one in the bottom in this table, may not converge in very dense environments with large number of users. However, it has very low signaling overhead, but it suffers for exerting many computations and a very high latency to reach convergence. One of the main limitations of multi-agent reinforcement learning is the challenge of coordination and communication overhead, especially in environments with a high latency or variable connectivity. So techniques such as decentralized training with centralized execution help address these issues by allowing agents to train in a shared environment while making independent real-time decisions. When we are able to decouple the training from the execution, then multi-agent reinforcement learning can support distributed decision-making without the overwhelming the network infrastructure. This is essential for time-sensitive applications as coordinated sensor networks, disaster response, and where the efficient resource usage and rapid adaptation are critical. While multi-agent reinforcement learning addresses the coordination of multiple agents in dynamic environments, MTC applications also benefit from other advanced reinforcement learning approaches, like offline reinforcement learning and distributional reinforcement learning. So differently from multi-agent reinforcement learning, which focuses on and traditional reinforcement learning, which focuses on real-time learning and coordination among agents in the multi-agent case. Offline and distributional cases are designed to optimize individual decision-making by learning from pre-collected datasets and understanding real-world variability. So these methods offer reliable, robust training for applications that require both efficiency and adaptability and safety and scalability under uncertainty. So we can have here one example of offline reinforcement learning here in figure C on the bottom. So we have the actions. So an agent has explored collected this data set, and stored in the buffer. Now we're taking this buffer and exploring further actions here and learning the optimal policy. So it differs from the off policy deep reinforcement learning, as this is interacting and storing, and the main difference here is that this is completely done offline, this process, and in here we have some real-time components. So I am collecting information, updating the buffer, and then using the buffer plus the new information to do the updates and trying to identify the optimal policy. In here, I am defining the optimal policy from offline datasets. So offline reinforcement learning enables a model to train using a fixed dataset without continuous environmental interaction, and that's the main difference to traditional reinforcement learning. In traditional online reinforcement learning, models rely on real-time feedback from the environment to update policies and improve decision making. However, this approach can be costly and also unsafe in MTC settings in terms of privacy. So, where these devices are operating under complex and uncertain conditions. Offline reinforcement learning mitigates these concerns by using historical data to learn optimal policies. It eliminates the need for live data collection during training. And then that is the main difference between figure B and C here. So during the training, we are not collecting any real-time state updates and rewards and actions from the agent. We are only relying in offline reinforcement learning on what is available in the buffer. This approach is beneficial for applications like predictive maintenance or industrial IoT, where data collection can be expensive and the safety considerations are paramount. So offline reinforcement learning is also advantageous in MDC systems where frequent data transmission is impractical or the device lack reliable connectivity. Another example of this is in the O-RAN type of networks, where we can collect the data from the operation during the day and then do the training in an offline mode during the less active hours of the network, and then inform these agents of the new model parameters and the optimal policies, so that they can be updated throughout the active times of the network. So by enabling policy optimization offline, these AMTC networks can leverage the strengths of reinforcement learning without the logistic or operational burdens associated with online learning. So this would be the main advantage of offline reinforcement learning. We also have distributional reinforcement learning. So what is the key point here? In distributional reinforcement learning, we add one layer more of robustness by focusing on distribution of potential outcomes rather than the average rewards. So the difference between figure B and figure D here, this column, is that in here we have the state, the policy, we look at the average reward, we store that information together with environmental state reward actions and everything that this user is collecting in the buffer. We use it as a point estimate and feed this neural network and then do the state update policy. In here, we do something similar. However, instead of only looking into the average, which would be somewhere here for whatever distribution that we are looking here, we do look instead into the risk measure. So in portions of the distribution which are relevant for us. And we are looking over the whole distribution, not only on a single point estimate. This gives us a lot of flexibility. However, as usual, it introduces quite a lot of complexity as well. So that's what we will be looking here. So traditional reinforcement learning methods aim to maximize the expected rewards, which is known to work well in stable environments where there are not very large variations in the environment. but fall short when applied to highly uncertain scenarios, which is the case for MTC applications. We have unpredictable device connectivity and unpredictable device activity, network quality changes over time, and that those are limitations that come to that limited performance of traditional offline and online reinforcement learning. So distributional reinforcement learning comes to solve or address this problem. For instance, in this case of the UAV setup, we have extended that model to include distributional reinforcement learning and offline reinforcement learning here in this paper that was recently accepted to Transactions on Cognitive Communication and Networking. This was in collaboration with Professor Simeone from and our main part of our main results here is to show that part of our main results in this publication here is to show that in the scenarios where we have a risk, for instance, as in this UAV case that we saw in this previous scenario here, whenever the UAV enters this area, it receives a severely bad penalty. However, the UAV may risk to enter this area, so we give this option to the UAV in case there is the risk of receiving a very large penalty, but there is also the benefit of serving these users with much higher reliability. In this case, in this particular case, would be lowering the average AOI significantly. And that's what we show, that whenever we give this and we quantify this risk measure, we are able to serve or better serve the users in this particular work, and many other aspects that were covered there. So here we have one example illustrating these different algorithms. So we have traditional reinforcement learning, we have grid algorithms, and we have these different DPQ networks and variations related to offline and distributional reinforcement learning. What we want to primarily show here is that this is the online counterpart. So we have different epochs of the algorithm. We achieve convergence, and then here we then allow the CQR algorithm to run and achieve convergence up to this point, and we can see that we are able to operate with better performance than the counterpart, the online reinforcement learning. So by learning from distributional data, devices can adopt policies that are efficient under normal circumstances and resilient to unexpected challenges. Both offline and distributional reinforcement learning provide robust solutions to some of the inherent challenges of offline and the traditional reinforcement learning methods. Offline reinforcement learning enables safe, cost-effective training, while distributional reinforcement learning ensures stability and reliability even in uncertain and dynamic environments. These methods complement multi-agent alternatives and allowing for development of robust policies for individual agents within larger multi-agent framework. Combining these techniques in MTC can achieve high efficiency, adaptability, and resiliency, and addressing the complex and diverse needs of next generation wireless networks. So we foresee that offline and distributional reinforcement learning will be key tools for the next generation of wireless systems. And one of the main applications for this would be all-RAN based setups and the optimization of the X and R apps functionalities within this type of architecture. So, in a nutshell, multi-agent reinforcement learning enables distributed decision making. It's versatile, and we can have cooperative or competitive policies and hybrid policies where they can agents can adopt to cooperate or compete. We are able to have high adaptability to changing environments. However, it requires quite a lot of coordination overhead. The scalability to large and complex networks also is somewhat limited because of the high dimensional space action spaces. And then we have the limitation of the training, particularly for the online case. If we then move to the offline reinforcement learning, we have some advantages that is enable safe and cost-effective training. And then the distributional reinforcement learning ensures stability and reliability. However, we also have then to collect the training, and we have additional complexity to run these types of models. Next, we will discuss a few of the challenges and that we foresee for the next in moving forward with the development of 6G. So while distributed learning methodologies such as multi-agent reinforcement learning, offline reinforcement learning, and distributional reinforcement learning offer promising solutions for MTC networks, they also present several pressing challenges that must be addressed for successful large-scale deployment. These challenges range from privacy and security to scalability, standardization, and maintaining model accuracy across diverse environments. We will touch a few of those that I see as most relevant and are most related to my current research. Concerning the scalability and computational efficiency, one of the most significant challenges is the scalability. MTC networks are expected to expand to billions of interconnected devices. And predictions foresee more than 5 billions of devices by 2028 and tens of billions of devices by early 2030s. So, and then these devices have several differences that are quite heterogeneous in terms of computational power, connectivity, and energy resources. As these networks grow, maintaining synchronized model updates across heterogeneous environments becomes increasingly complex, and distributed learning methods such as multi-agent reinforcement learning and as well as federated learning require substantial computational resources. So training these models can become computational prohibitive for resource-limited devices, and collecting this data is also prohibitive, leading to delays and reduced system performance. So one way to overcome this is to introduce lightweight learning models, adaptive algorithms, merging these different architectures that we discussed today into new frameworks so that we may have energy efficient training techniques and better performing techniques in terms of data acquisition or data training and performance. Asynchronous updates and hierarchical learning architectures offer the potential solutions are also potential solutions because they enable partial synchronization across devices and reduce dependency on single global model. However, achieving consistent performance this scale without compromising efficiency is still a challenging area, and so it would be worth investing some more research efforts in this direction. Another point is adaptability to dynamic environments. MTC networks, they often operate in dynamic and unpredictable environments where network load, device connectivity, and resource availability can change rapidly. In scenarios like smart agriculture, autonomous vehicles, fleets, devices must adapt their behavior in real time, adjusting to sudden shifts in the network connectivity or environmental changes. So multi-agent reinforcement learning and distribution reinforcement shown are promising solutions in enhancing adaptability, enabling agents to adjust policies based on real-time feedback and varying reward distributions. However, developing models that can generalize effectively across both stable and fluctuation conditions is very challenging, and that deserves further research. So robust learning frameworks that incorporate these elements of adaptability and stability are essential. And methods for managing the trade-offs between the exploration and exploitation in these dynamic environments are still needed in the recent in the literature. Concerning privacy and security, we have only discussed about the models that preserve the raw data, but it is still quite a large challenge, especially as the network grows. There are more points for attacks, and techniques like differential privacy and homomorphic encryption are being explored to secure data during distributed learning process, allowing for models to train without exposing its raw data. Implementing these techniques in very large networks with varied MTC devices, heterogeneous devices, is very challenging though. And finally, but not least, communication overheads and latency. Distributed learning inherently involves communication between devices, which can lead to significant overhead in MTC networks, especially in the case with limited bandwidth or high latency connections. So, multiple agent reinforcement learning and federated learning approach require frequent exchanges of model updates, which can overwhelm network. This would be especially even more complex in rural and remote areas with poor connectivity. So techniques such as communication efficient model aggregation, update sparsification, and model compression are still needed and need to be revised and further developed. Decentralized learning methods that minimize reliance on central services are also gaining traction, especially in applications with low latency. By reducing the frequency or size of the updates, this approach helps balance the communication needs and the network's capacity. But further optimization is still necessary to ensure seamless performance across varying connectivity conditions. And in here, over-the-air communication is also one of the significant areas to be integrated with these different approaches. So further directions and research focuses. I hope this tutorial gave you some ideas of potential and interesting research directions. Distributed learning methodologies continue to evolve. Research will need to focus on overcoming this critical challenge that we discuss here to fully realize the potential of the MTC in the next generation wireless networks. Developing algorithms that can process large-scale heterogeneous data more efficiently are crucial, especially while minimizing communication and energy consumption. Future advancements in privacy preserving techniques, for instance, in federated distillation, secure multi-party computation, and are pivotal or will play a pivotal role in balancing security performance in distributed MTC applications. Additionally, integrating distributed learning with AI to sudden shifts in how information continue to evolve. So that's all I had to say on distributed reinforcement learning for MTC. If you'd like to follow up more on our activities, please don't hesitate to get in touch. You can also visit my webpage and you'll find our most recent publications on this topic. Hello again. So here we will be talking about satellite IoT. Again, I would like to highlight here that this is a collaborative effort, and here are a few of my key collaborators in this topic. So we'll start with a brief overview of what is satellite IoT, and I would like to highlight that part of this research is coming in this book, and part of the content of this tutorial is also from this recent publication that we have, that is the integration of MTC and satellites for IoT towards 6G era. If you want to know more about the book, you can visit satelliteiot.org. And in this book, we cover all the different aspects of the integration of MTC and satellite networks. So covering the drivers, the use cases, the end-to-end support, channel models, the constellation designs that are necessary for new space applications, the physical layer aspects of MTC and satellite integration, MAC protocols, networking, onboarding capabilities of the satellites, then software-defined networking, the aspects of security, the simulators and tools that are needed for analysis of this integrated network, the business aspects, regulation, and as well standardization. So we have received inputs from both academia and industry and compiled this into this recent book. So for more details, you can visit satelliteiot.org. So satellite IoT is pivotal in realizing the vision of 6G networks, driven by social, economic, and environmental factors. These drivers highlight the need for global and equal connectivity and underscore the technical and ecological requirements that shape the evolution of satellite communication systems. So one of the key motivations for satellite IoT is that it enables global coverage even in areas where we have, especially in areas where we have little infrastructure or deploying infrastructure is impracticable or unreliable. So that would enable people and also devices to be connected uh, and have and support connectivity in those regions, and that will help to reduce or the digital divide. So one of the key, let's see now what are the motivations behind this towards this integration. So the rapid growth of IoT, Internet of Things, is transforming the connectivity landscape. With billions of devices coming online across diverse sectors such as healthcare, agriculture, transportation, and industry, the demand for seamless connectivity grows, and traditional terrestrial networks struggle to meet the coverage and scalability requirements, particularly in remote and underserved regions. And it is in here that satellite IoT plays a pivotal role in shaping the future of 6G. For instance, in this plot here, that is based on Ericsson research projections, we can see that at about 10 years ago we didn't have that much cellular IoT connectivity, and now we are expecting to have several billions, about 5 billion devices connected, and towards 2030 this number should reach tens of billions of devices, and that is only considering IoT cellular IoT solutions. If we include low power area networks, then this number grows by 10 times. So satellite IoT addresses key challenges by providing global and equal connectivity, bridging the digital divide, and supporting services that terrestrial networks alone cannot sustain. Whether connecting remote sensors in agriculture, enabling autonomous vehicles, or supporting critical healthcare applications in isolated areas, satellites ensure reliable communication where terrestrial networks fall short. IoT continues to expand, with projections of trillions of connected devices in the coming decade. Satellite IoT ensures that 6G networks are scalable, but also inclusive and sustainable. It is key to unlocking the full potential of IoT, ensuring that connectivity reaches every corner of the globe, from urban hubs to the most remote regions. So to do so, there are already constellations with thousands of satellites deployed. Currently, the number is close to 12,000 LEO satellites, And Starlink alone has the majority of those satellites, which is about 7,000 in operation in low Earth orbit. EUTELSAT, for instance, is an operator, and as well as other players, they have plans to expand their constellations, and new companies are emerging in this domain. For instance, EUTELSAT is the first hybrid operator operating with GEO and LEO satellites, and they are expanding their constellations. And the recent established Creepier solutions that is based on Amazon. And then also Starlink that started operating a few years ago and now has the majority of the market or in the majority of the satellites in this domain. So what are the drivers behind this innovation and this demand? Satellite IoT is not only about connectivity, it's also about social, economical, and environmental factors drive it. So the social aspects, they aim to bridge the gap in the digital divide, supporting equality in services and advanced human-centric applications. Economic aspects offer cost-effective solutions for remote and vast areas where terrestrial infrastructure is impractical, and environmental, supporting sustainable development, avoiding ecological disruption, and advancing energy-efficient technologies. So as we can see here in this graph, if we go further into each of these areas, we can say that from the social drivers, one of the primary motivations for satellite IoT is bridging the digital divide. That despite the advancements in 5G, a significant portion of the global population and even larger share of machines lack access to reliable connectivity. Satellite IoT enables seamless communication across remote and underserved regions, from isolated islands to vast rural landscapes. This connectivity supports societal goals aligned with the UN Sustainable Development Goals, including equality in education, remote healthcare, and disaster management. By providing resilient machine-type communication, satellite systems ensure that services relying on IoT devices, such as autonomous sensors, robots, and vehicles, operate efficiently and reliably. If we take a look here now into the economic factors. So building terrestrial networks is in remote areas such as the Arctic or deserts or is often economically unfeasible. Satellite offers a cost-effective alternative to connect to these regions. So it is here in our particular case here, building infrastructure in the northern parts of Finland are quite cumbersome, and in the North Arctic regions or in the Arctic region, northern Finland, including the sea, it is quite underserved in terms of connectivity. So satellites IoT would be one solution that could enhance the connectivity for those regions, enabling new services and new businesses, and also providing coverage for vessels traveling and passing through the North Sea. And in the context of Brazil, it would be providing or enabling that remote regions in Brazil, and especially remote areas such as in the Pantanal or in the Amazon region, could be covered and bringing connectivity for isolated communities and enabling several types of services such as distance learning and remote healthcare. So by leveraging satellite-based solutions, operators can provide connectivity at a fraction of the cost of deploying the terrestrial network. Standardization further accelerates the adoption, ensuring interoperability across diverse networks, and market expectations for seamless, affordable connectivity drive the integration of satellites into global 6G ecosystem. This offers a scalable and economically viable solution for operators and users. Last but not least, the environmental drivers. So environmental sustainability is a critical driver for future satellite IoT systems. Unlike terrestrial networks, which may disrupt fragile ecosystems during construction, satellites provide connectivity without physical intrusion. Additionally, advancements in satellite technology uh, focus on reducing space debris, enhancing energy and spectral efficiency, and mitigating the environmental impact of operations. For example, deploying satellites instead of terrestrial towers is economically uh, ecologically sensitive areas, ensures the connectivity while minimizing ecological harm, for instance. So satellite IoT also enable numerous 6G use cases that demand seamless global coverage. Applications like autonomous mobility in air, sea, and ground domains rely on robust satellite IoT connectivity to support millions of sensors, actuators, and edge devices. The systems require a three-dimensional network to deliver the scale, complexity, and quality of service needed for these advanced use cases. From remote maintenance of ships to autonomous vehicle coordination, satellite IoT underpins the connectivity required for the next generation of machine-type communications. We can dive a little deeper into these use cases. So satellite IoT is rapidly growing, with projections showing an impressive annual growth rate of 22%, reaching over $6 billion American dollars by 2031. This growth is fueled by the unique capability of satellites to provide global coverage, making them indispensable for a wide range of applications. So we can then have these use cases classified in a few types of services. So the first one that we want to discuss is the coverage challenging services. So the first class includes services that operate in remote regions where terrestrial infrastructure is unavailable or unfeasible. So this can be agriculture, so monitoring of soil conditions, weather, and crop health in rural areas far from cellular networks. This would be the case, especially in the farming regions in Brazil. Nature monitoring, tracking wildlife, managing forests, and observing environmental changes in remote or sparsely populated areas. So we have been collaborating here in Finland, in particular, with the tracking of wildlife. Herds of reindeers are monitored, and we have been assessing the option of using satellite IoT associated with LoRa to do this tracking. We have also discussed the possibility of tracking wildlife in Botswana. So tracking the population of cows and wild and other wild animals, also using satellite IoT type of connectivity. And then the same applies in Brazil, where we could use this type of solutions to monitor wildlife, monitor forests, and have better input on these specific regions. So not only monitor, but be able to inform decision makers with more reliable data. And in this particular case, we also have industrial services supporting, for instance, oil and gas operations in isolated regions and offshore rigs. where the infrastructure deployment is impractical. So this also would be particularly relevant for Brazilian scenarios due to the large number of oil rigs that are in the coast, and then we could provide additional support for maintenance or plain connectivity of these infrastructures. And then a last point that we can mention here is maritime IoT, connecting ships, fishing vessels, and other maritime operations, where the dynamic nature of the environment makes static infrastructure unfeasible. So this would be a key enabler for this domain, having the connectivity with the satellites. So this class leveraged satellite connectivity to overcome these challenges posed by sparse populations and infrastructure gaps, ensuring reliable communication and data flow in the most remote areas. We have also ultra-mobile applications. So in this case here, the second class encompasses the use cases requiring high mobility, where devices or systems frequently move across regions or countries. So the classical example here is transportation networks. So tracking a container shipments and managing fleet logistics as they move globally. So this would be facilitated by satellite IoT. Aerial networks connecting high altitude platforms, drones, and other um, unmanned aerial systems would be facilitated with satellite IoT, providing for them reliable connectivity to operations in certain areas, or broad connectivity enabling, for instance, UAVs to navigate for to be controlled over longer or larger coverage areas. The motivations for these satellites here is twofold. So first, the systems often operate in areas with poor terrestrial network availability, similar to the previous class. And two, even where terrestrial networks existing, roaming across multiple, often non-compatible networks with different spectrum regulations can be difficult and costly. So satellite IoT provides a seamless global solution for these highly mobile scenarios. And the next class focuses on the use cases where high communication reliability is essential, therefore the dependability critical applications. But these are not necessarily with ultra low latency. So to make a distinction to the ultra reliable low latency communication use case in 5G, and the main point here for this type of communications, dependability critical, is emergency management. So supporting disaster recovery efforts or maintaining smart grid operations during outages. And as also as a backup communication, offering satellite-based communication as a fallback when terrestrial networks fail or are disrupted. Which may be the case during natural disasters. The terrestrial infrastructure might be compromised, so satellites can provide a lifeline for communication and coordination. So this dependability makes satellite IoT critical for emergency response and recovery scenarios. So it's important to note that some of these applications, like smart grids or oil and gas pipeline monitoring, they have some overlaps and may belong to belonging to multiple categories. For instance, they may need coverage in remote areas while also requiring a high reliability during emergencies. So there is quite some overlap over these different classes and the needs depending on the application. We can highlight here a few of the domains and use cases for satellite IoT, as we discussed a few of them already. and then the related references here. And in this table 2.2, we want to highlight a few points. So satellite IoT is proliferating, with operators worldwide offering innovative connectivity solutions for diverse applications. So here we have a few highlights. So according to the data summarized in this table 2.2, multiple satellite IoT operators are leveraging both proprietary and standard-based technologies. So in this case, cellular IoT, and in some others, a low power wide area type of solutions. Most of the constellations used currently by these different companies are on low Earth orbit satellites, with operators deploying a few to several hundreds of satellites. And depending on the application requirements, some services also rely on geostationary Earth orbit satellites, such as the ones used for GPS. So these operators cater to various use cases across domains, such as maritime and transportation, environmental monitoring, industry, and agriculture. A standout feature of satellite IoT services is that their suitability for massive MTC, characterized by the infrequent transmission of small data packets from numerous devices. So this is one point that we mentioned is characteristic of massive MTC, that short packets, short updates are sent by a very large number of devices. So you have a very large number of active devices in the network, but their transmission activity is very sporadic, and this is quite cumbersome to allocate resources and do effective RAID resource management for this very large number of users. Even though as we can see here in this table, even though the subscription costs for satellite IoT services are higher than those for cellular IoT, the cost per device can be competitive, especially for applications requiring infrequent data transmissions, where the costs can even be below a few dollars per month. Satellite IoT is also evolving to integrate seamless to be integrated seamlessly with the terrestrial networks. So there are already the emergence of hybrid modems, such as this Orbcomm ST9100 and Centec LR1120. So these devices, they were launched recently, 2-3 years ago, and they support both terrestrial and non-terrestrial communication. So they enable robust and flexible connectivity. And such integrations highlight the push towards seamless operation between satellite, high-altitude platforms, terrestrial networks, and non-terrestrial networks, NTNs. From the standardization side, from 3GPP, as part of the 5G NR specifications, it is accelerating the adoption of satellite IoT. So satellite EMBB serves moving vehicles, disaster recovery, in areas without public network coverage, while satellite MTC connects IoT devices across a wide geographic area, so very large areas, including agriculture, road transport, energy monitoring. Emerging technologies such as SDNs and network virtualization functions and edge computing further enhance the flexibility of satellite IoT. We can see also that some of the satellite IoT key performance indicators, as we can see in this figure, and And these indicators are essential metrics used to evaluate the network performance, enable comparison, and set development goals and guide the technological evolution. So these KPIs focus on technical performance for satellite IoT and the next generation networks. They are increasingly tied to the value-oriented indicators, aligning with the social and economical demands and also the drivers, the social and the environmental and economical drivers. So the ITU define 8 KPIs, as we can see here in this figure, for 5G in 2015, many of which remain critical also for satellite IoT and 6G. So there is already a revision of these and a discussion for what will be the KPIs targeting 6G. And we during the preparation of this book, prepare this graph as we expect these KPIs to still play a very pivotal role in the next generation. So NTNs, including satellites, have unique requirements to ensure seamless integration in terrestrial systems. One of them is continuity, guaranteeing the uninterrupted services as users transition between terrestrial and satellite networks. And this allows us to ensure reliability and quality of service. There is also ubiquity, extending connectivity to underserved and unserved areas, enabling coverage in remote and challenging regions. And the other one is scalability, supporting large-scale broadcasts and multicasts while efficiently managing many dedicated users. So, for instance, in 3GPP release 18, cellular-based satellite IoT access targets uplink and downlink data rates of 10 kilobits per second and 2 kilobits per second, respectively, while accommodating user speeds up to 100 kilometers per hour and supporting a density of 400 users per square kilometer. So this gives an idea of the targets that are already present in release 18, which is the current release, and the efforts that have been put towards attending these demands of a high mobility or vehicles moving with fast speeds and the types of rates that are expected for this type of service. As you can see here, the data is much lower than conventional eMBB broadcasts, but for MTC applications, these rates are quite fine. And the number of users here, 400 users per square kilometer, is a quite good indicator of the number of users that are expected to be served. We expect this number to grow, so to serve more than 1,000 users per square kilometer in the next generation, and that is already possible with some low power wide area solutions. So future networks must expand beyond traditional point-to-point performance metrics, so to meet these diverse demands. And new end-to-end measures inspired by reliability theory and other theories that capture the large-scale network behavior are needed. So, for instance, network availability, energy efficiency, dependability, and affordable coverage could be this type of new metrics. But those also need to be studied and proposed more carefully. So to address this need for an end-to-end performance metrics. So this shift in perspective and associated with this need for these new metrics aligns with the anticipated integration of advanced capabilities like sensing, intelligence, and local computation into the next generation networks, so that it will ensure this advancements, technological and societal, meeting the technological and societal needs. Next, we will talk about a few definitions of satellite IoT and how the networks are built on critical components that ensure the seamless data transmission and efficient connectivity and global coverage. So one of the primary components is the end devices and satellite terminals. So end devices, also known as user terminals or satellite terminals, are essential components that transmit and receive data from satellites. So here they are illustrated by this symbol here. And this enables this device to connect to the satellite. Then the satellite will be able to connect to a ground station that is represented here. They also may have the case of satellite terminal, where devices connect to a ground satellite terminal that will then be equipped to transmit and communicate with the satellite. So this device might have better antenna gains, better, more capable hardware than these other types of devices. So this will depend on the type of architecture that we are discussing. We will see more details later. So these devices, these end devices, are designed with varying capabilities based on the application requirements. So they are often compact battery-powered devices, especially for machine-type communication applications. And for instance, they may be devices like LoRa 1 Class A terminals that prioritize energy efficiency. And these devices can have power saving schemes that maximize battery life, so they remain for in deep sleep mode when they are inactive. Conventional satellite terminals are devices that are similar to the ones used by Starlink. So they require a continuous power supply, making them suitable for applications with higher data demands and constant connectivity needs. So that would be something similar to this device here, where you have a ground terminal that collects the information from the neighboring devices, and then this device here is the hub that will be connecting to the satellite. The satellites, now if we look a little here on the satellites themselves, they can act as wireless transceivers orbiting Earth, so pivotal in enabling direct-to-satellite IoT. And we will see what is direct and indirect to satellite when we discuss the architectures. So their orbital height and payload influence their cost and performance. We can mention here that the nanosatellites, they are special satellites that weigh less than 10 kilograms and are cost effective and quick to develop due to their affordability and compatibility with LEO deployment. So this low Earth orbit here, that is around 500 to 2000 kilometers from the ground. These satellites, these nanosatellites, are quite widely used for direct-to-satellite IoT. One of the common types of satellites here is then the CubeSats. So they are standardized nanosatellite designs that are constructed in units. So it standardizes the units with measurements proportional to 10 by 10 by 10 centimeter satellite. So they are literally cubic satellites, and then the measures are units proportional to this base dimension. And CubeSats are commonly launched into the LEO, and they are often, well, they are lightweight, and they have also limited lifetime. So there is a preference for small and lightweight satellites. It stems for their lower launch costs. So the less heavy, the lower the launch cost, and the reduced development in time, and also the suitability for dense satellite constellations that you can deploy many of these smaller satellites to provide good coverage globally. Another nomenclature that is used for some of these terminals is gateways. So gateways are intermediate nodes between end device and network servers. So we might have here, for instance, this, we can perceive this point, this node here as a gateway. So it's a gateway connecting the ground devices. The ground devices connect to the gateway, and then the gateway connects to the satellite. And then depending on the architecture, the gateway might be placed here. So on the ground, or it might be present as a function or as a part of the satellite. And it's also related to the payload. We will see this in the next slide. Then another component here is the ground station that is illustrated here, depicted in this figure by this symbol. So the ground stations are F-based radio transceivers that facilitate the communication with satellites. The main the main difference between ground stations and other end devices is that they control the satellites and monitor telemetry data. They are able also to configure onboard satellite radios, ensuring optimal operation. And the ground stations are an integral to managing the satellite constellation and enabling seamless data flow between satellites and terrestrial networks. And usually the link between the ground station and the satellites is a dedicated link using different technologies than cellular-based solutions. Then the communication links, they have a different nomenclature as well. So there are three types of links. There is the service link that connects end devices to satellites. So these blue ones would be service link, enabling the data transmission. There is the feeder link that facilitates the communication between satellites and ground stations. So this green link here. And then there is also the inter-satellite links, so information that is passed from satellite to satellite, and connecting the constellation, allowing data sharing and coordination among these different satellites. These links ensure the integration of multiple satellites into a cohesive constellation, providing robust and reliable global coverage. So now in the next slide we will talk about the payloads, and then we understand why there is some differences between these types of operations on the satellite and what are the satellites capable of doing. So we have basically two payload modes. So there is the transparent payload, known as bent pipe architecture. So transparent payload acts as an analog repeater, and we can make a parallel here to amplify and forward relay. So they filter, amplify, and relay signals without demodulating or decoding them. They are simpler and cost-effective, but have lower spectral efficiency. So similar to amplifying forward relay in terrestrial networks. In this case here, we don't want to add additional complexity to the satellite, We can only use the radio that is already available there, or we don't want to deploy additional complexity to consume energy from the satellite. So that's a very basic and simple solution. So it acts as a basic relay, just reshaping the signal. And then we also have the regenerative payload. In this case, the parallel would be to decode and forward type of relay. This feature onboards processing capabilities, so it's a more robust processing capabilities, enabling signal demodulation, decoding, error correction, and then re-encoding. And so these regenerative payloads enhance spectral efficiency and overall system performance, making them ideal for advanced communication requirements. So the main difference here is if the gateway is the satellite is acting as a gateway or as a base station. So as a gateway in LoRa type networks, as a base station in in cellular jargon. So in both cases, they might receive just information and work primarily as a relay. That was the initial deployments or the initial settings that 3GPP adopt. So to have transparent payload. But now with the new releases already on 18 and 19, regenerative payloads are being considered. So the idea is to have a satellite that has 5G capable would operate as a 5G capable base station, so has the functionalities of a base station on the satellite. And the same for a LoRa network, a low power wide area network, where the satellite is has a gateway and maybe even a network server deployed on the satellite side. So it receives the codes and then decides based on what was received, and then there is exchange of information between the satellite and the ground network. These satellites, as we mentioned, they operate primarily in this low Earth orbit that is positioned between 500 and 2,000 kilometers. And the main advantages of this lower orbit is that there is minimal propagation delay, so less than 10 milliseconds. The propagation losses are much smaller as well because they are closer to the ground. And the costs for launching and deploying the satellites is much smaller. So this enables the feasibility of direct to satellite connectivity solutions, and without requiring excessive transmit power. The other orbits, they operate. Medium Earth orbit operates between 2,000 and 35,000 kilometers, and is a good balance between coverage and latency. So the higher you go on the orbit, the larger is your footprint on the ground. You can imagine that the satellite is projecting its shadow to the ground. So the larger it is, the higher the altitude of the orbit, the larger would be this shadow. So that's why we need several thousands of devices on LEO orbits, so to be able to provide coverage everywhere. And fewer are needed if we consider geo satellites. One of the disadvantages of this is that in the geostationary satellite, as the name suggests, these satellites are mostly static relatively to the ground. So they still bounce back and forth around the position that they are, but they are maintaining this the footprint of coverage on the ground, and therefore their velocity they have they are stationary on that position compared to the ground. In these other cases here, the LEO satellites and the MEO satellites, they are moving at very fast speeds. So especially in the LEO case, they are moving very fast. So several kilometers per hour. And then that generates several issues, as we will see later. So therefore, LEO satellites, they dominate the satellite IoT landscape. We have more than 10,000 devices or satellites already deployed in orbit, and that is mostly because of the cost effectiveness of launching and deploying these satellites. Satellite IoT is a rapidly evolving field that leverages a diverse set of technologies and addresses the growing demand for global connectivity. So 3GPP standardized a few technologies, for instance, the narrowband IoT and more recently the 5G new radio. These are common or are being considered. NB-IoT is already seeing some measurements and is one of the candidate technologies to compete with LP1 solutions in this satellite market. So NB-IoT is a 3GPP low power wide area network technology for massive MTC. It operates in a licensed frequency band. It uses simplified LTE-based procedures for efficient data transfer. A major milestone concerning NB-IoT was achieved when MediaTek and Inmarsat successfully tested NB-IoT connections with GEO satellites, demonstrating the feasibility for the satellite IoT in that orbit. And more recently, companies like Satelliot, Oki Technologies, and Mediota are deploying NB-IoT for satellite IoT services. And the data rates, they range from 30 kilobytes to 60 kilobits per second. 5G New Radio. So 5G New Radio supports enhanced mobile broadband, ultra-reliable latency communication, and MTC. And the NTN component includes L and S and K band frequencies, which have been proven for satellite communications. And then there are a few trials by AST Space Mobile and Link Global that have already demonstrated successful use of 5G satellite calls and messaging services using standard mobile devices. More recently, with the 5G RedCap reduced capability in release 17 and ongoing developments in release 18 and 19, 5G NAR is becoming increasingly versatile for mid-range IoT applications. So this is a new solution that is addressing particularly IoT scenarios where we have demands for higher data rates. So 5G RedCap is one of the candidates for being a standalone solution focusing on MTC. So here we have a few of these companies that we mentioned that are all already operating and have LoRa or proprietary solutions, and or also NB-IoT, for instance. Satelliot is one of them that are using NB-IoT based solutions. On the non-3GPP low power wide area networks, the main solution here is LoRaWAN, because they are energy efficient, low cost, and they have very long range communications on the ground and also for the satellites. So if we talk about LoRaWAN, it has emerged as a leading protocol for satellite IoT with more than already 20 active LEO satellites transmitting LoRa packets. Operators like Lacuna Space, Norby, and Fossa have collectively processed over 8 million LoRa packets through ground gateways. So unlike 3GPP solutions like NB-IoT, LoRaWAN operates in a license-free spectrum, making it cost-effective choice for low data rate applications. LoRaWAN gateways are also commercially available for deploying private networks, and that is also an advantage over other non-3GPP solutions and also 3GPP based solutions like NB-IoT. Recently, LoRaWAN introduced a new modulation called Long Range Frequency Hopping Spectrum, LRFHSS, and is designed to support terrestrial and satellite IoT, enhance uplink performance for direct-to-satellite communications. And then on other solutions, for instance, Starlink, their constellation operates with a private protocol. We know that the downlink terminals speeds can go up to 200 megabits per second, and the uplink speeds are around 25 megabits per second, and the latency is usually below 100 milliseconds. And it's expected that future Starlink satellites, they might align with 3GPP specifications and enable direct connectivity from the cellular terminal on the ground to the satellite. A key trend in satellite IoT is the integration of 3GPP and non-3GPP technologies. So creating these hybrid systems, as we mentioned, Centec and Orbicon have already launched devices that or chipsets that support both terrestrial and non-terrestrial connectivity. So they enable seamless operation across diverse environments. For the rest of this talk, we'll be focusing mostly on LoRa, so I will give you a very brief introduction to what LoRa is and what are the key characteristics of the new modulation, the FHSS. So LoRa is short for long range and is a wireless communication technology based on chirp spectrum, CSS modulation. It offers a long-range, low-power connectivity and is one of the most popular solutions for IoT in many domains, especially low-power, wide area type of networks. So it's based on the notion of a spreading factor, which is called SF, and the values range from 7 to 12. So higher SF, let's say 12, increase robustness against noise, enhancing gateway demodulation capabilities, and the signals with different SFs can be received simultaneously due to their quasi-orthogonal nature. So each SF operates almost as an orthogonal channel. The LoRa bandwidth can range from 31.25 to 500 kilohertz, and they affect then the transmission range and the data rate. So, and then the modulation alphabet is a function of the SFs. So for better data rates, for faster speeds, you would use lower data rates, lower SFs, say SF7, and for high robustness, you would use SF12 for your modulation. LoRa also supports a mode that is called low data rate optimization, LDRO, And the main objective of this is to combat the Doppler effect. So if this is even talking only about the terrestrial networks. This is also enabled for satellites, but the main objective here would be to do rate allocation or operate with for some flexibility in terms of rate, to be able to adapt or reduce the modulation alphabet size, increasing the frequency separation between the chirps, so improving the robustness to Doppler. And however, this comes at a cost that you would be operating either more reduced rates. LoRa has this framing structure that is exemplified here. So as you can see, is a very simplified frame. It has a preamble, a header that operates with a given code. This is only 20 bits and has some CRC. And then the coding rate for the physical payload and the CRC is also different from the coding rate of the header. This physical payload has a MAC header, a MAC payload, and if we look here, we can see here that the amount of data that is able to be transmitted is quite small. So the packets overall are very small. The preamble is usually used for the synchronization. So is typically using 12 symbols, but it can go up to more than 65,000 symbols. The header contain the payload length, the code rate, and the CRC information. And then the payload, it's where the data is, and is usually of 13 bytes. So as you can see here is very small. So LoRa's unique features such as adaptive bandwidth and spreading factors enable robust communication. And then they are already proven and well studied for terrestrial networks. There are also some studies for non-terrestrial networks integrating LoRa to satellite communication, and there are satellites operating transmitting LoRa packets to the ground. We even have a antenna and devices at CWC collecting these packets that are broadcast by the satellites that pass over Oulu, and then we can collect this telemetry data with their position and a few other features that are broadcast by these satellites. The other modulation that was recently introduced is called long-range frequency hopping spreading factor. LRFHSS is an advanced modulation scheme integrated into the LoRaWAN protocol and is designed to enhance the scalability, robustness, and network capacity for IoT applications. The modulation is based on a Gaussian minimal shift keying. It operates with a bandwidth product of 1, so that ensures efficient and reliable communication. It has an intra-packet frequency hopping scheme, hence the name of the modulation, that supports up to 11 million uplinks per gateway per day, significantly higher than the LoRa capacity that is 1.2 million. It is more robust Doppler effects. It tolerates frequency drifts up to 300 kilohertz, and LoRa only can handle 120 kilohertz per second, and that makes it ideal for satellite IoT. And we will see why in a few slides. The frame structure, as we illustrated here in the figure in the bottom, it divides into header and a physical payload. the header is further split into subheaders. So the we call them fragments. So we break the header and transmit replicas of the header to improve immunity against interference, ensuring high reliable decoding at the gateway. And then the physical payload is then break into what is called fragments, several fragments. So the idea is to divide this payload into very small fragments, transmitting them across multiple subchannels. That's why the frequency hopping name. So we split the bandwidth that is available for this solution into very small packets and very small subchannels. And with that, we can spread the data and recover more efficiently. The main advantages is in terms of scalability. So it operates with very narrow subchannels, about 488 Hz, and enable efficient utilization of the spectrum. So in terms of the link budget, it matches the LoRa at an SF12 with 125 kilohertz bandwidth in terms of the link budget, but it is able to deliver 200 times more capacity. So it can serve a very much larger number of users. So in my group, we have been working into proposing and assessing the performance of different architectures. We have done some modeling, trying to understand the LoRa, the new modulation, FHSS, the effects of energy efficiency and reliability, and the Doppler effects. We also have developed simulation tools for LoRa 1, FHSS, and also LoRa and FHSS in MATLAB. And we have dealt with some analysis and performance analysis for different applications. And we will give a brief overview of these different aspects next, and highlight a few of the main research directions in this domain. So concerning the architectures, satellite IoT connectivity can be realized through two primary architecture options. One is called indirect to satellite, ITS, and the other is called direct to satellite. So as the name suggests, indirect to satellite, we communicate, the end device communicates to a gateway, and then this gateway or satellite terminal will be then transmitted to the satellite. On the other end, the direct to satellite, the end gateway or the end device, transmits to the gateway that is at the satellite. So they are deployed together. So we can see this as one single entity. And this is similar for both low 3GPP and non-3GPP type of solutions. So in terms of LoRa 1 types deployments, the gateway is the LoRa or FHSS gateway that is deployed on the ground or in the direct to satellite on the satellite. And in terms of 3GPP nomenclature, here would be the base station or the remote radio head or the GNode B that is collecting information from the devices and then would be enabled to connect to the satellite, or the GNode B is then placed on the satellite. So in the direct to satellite setup. Each of these approaches has its unique advantages and challenges, shaping their suitability for different use cases. So let's next explore these architectures and their associated trade-offs. So let's move to this figure here. We have all the configurations again. So in the indirect to satellite architecture, we combine terrestrial and satellite networks. This hybrid model, IoT and device communicate with a terrestrial gateway, which aggregates and forwards the message to the satellite via backhauling. So that's what we were illustrating before. So we collect the information here, send it to the satellite, and then the satellite broadcasts to the ground station. In the particular case of LoRa, we have one additional component that is called the server. So if we want the devices to connect the gateway will be then also connect to this network server, and then these entities connect to the satellite and the backhaul. So this would be one option. The other option is that there is only one gateway on the ground, but the network server is placed somewhere else. In this case here, the network server is placed on the satellite. And so the message comes from here to the gateway. The gateway simply broadcasts it to the satellite. The constellation will decide what to do with that message and then inform the ground station on the action that is need to be taken. And then on the other end, the satellite here only relays the message to the ground station, and then the ground station is the one that will be doing the decision. So in a LoRa network, the decision about what action needs to be done and the coding process and the extraction of information from the encoded packet here is only occurs in the network server. So we have different options of where to place this network server. For the indirect case. In 3GPP jargon, we have something equivalent. So this could be a remote radio head here that would be performing the whole decoding of the packet, and then is communicating with a LEO satellite and broadcasting this to the ground station that can be the cloud or the core network, and then for further processing. We can have the remote radio head placed not on the ground, also on the G node B, and then some processing be done here at the satellite level or over the constellation. And other option is that is the satellite acts as a relay, and this information is put forward, so acting as a backhaul link, as in this case here. Advantages of this ITS solution, indirect to satellite. So there is low propagation delay and path loss because the devices communicate with a ground node first, so the terrestrial network, and then a dedicated node will communicate with the satellite. So the shorter distance between an end device and a terrestrial gateway compared to a satellite minimizes the propagation delay and reduces the path. The path loss, ensuring more efficient communication. There is also more resilient modulation encoding. Relatively static nature of the terrestrial links allows for the use of energy-efficient modulation and coding schemes, and also reliable and stable channel, radio channel. So the terrestrial gateways offer predictable channel characteristics without the Doppler effect caused by the satellite link mobility. A few of the challenges, though. There is dependence on the infrastructure on the ground infrastructure. So deploying terrestrial gateways can be costly and in some cases is also impractical. For example, floating sensors in the sea or sensors in remote fragile environments like snow-covered mountains may not have access to support infrastructure. There is high energy consumption. Covering large areas with such as offshore wind farms may require multiple gateways, leading to significant energy demands for powering these gateways and the associated network management entities. And battery operation in this case might be a bottleneck as well. Security vulnerabilities, the reliance on terrestrial gateways introduce potential risks, such as the gateways may become a single point of failures, compromising the reliability and security of the system. On the other hand, we have then direct-to-satellite connectivity. In direct-to-satellite architecture, IoT end devices communicate directly with satellite onboard and on the terrestrial gateway, bypassing the need for terrestrial infrastructure. The main advantages is the simplified network topology, so the devices are able to connect directly to the satellite. The functions of a gateway or a base station are already embedded, or G-Node B are embedded in the satellite. And if not, then the satellite is able to operate with minimal functions and then broadcast, and the core functions are performed on the ground by the ground station. So these would be the two potential architectures also for 3GPP-like solutions. There is reliable connectivity in remote environments, so with good line of sight probability due to the satellite the DTS is well suited for dynamic and fragile environments, so where the terrestrial infrastructure is unavailable. There is potential for global coverage, so DTS enables wide area connectivity using optimized satellite constellations, offering scalability need for truly global IoT applications. Some challenges though. The massive connectivity management. Without the terrestrial gateways to aggregate or compress the data, satellites must process a large volume of uplink packets. So and this requires advanced onboard processing capabilities and strategies to mitigate interference. So this is one key research area in this domain. High path loss. The long communication distance between the end devices and the satellites introduces a significant path loss. In sub-gigahertz, LP1 technologies are less affected by the atmospheric attenuation. The path loss necessitates careful selection and adaptation of radio access technologies for MTC use cases. So this is not a big deal for sub-gigahertz, but for the medium-range bands, this is significant. And then there are other atmospheric effects that affect the use of different frequencies. So very careful selection here is necessary. The satellite mobility. So LEO satellites, they move very fast and introduce challenges such as the dynamic round-trip times and Doppler shifts, which complicate time and frequency synchronization. These issues are particularly critical for medium access control in the MAC protocols. There is also non-uniform frequency spectrum. The global non-uniformity of LP1 frequency allocations poses additional challenges, so satellites must support multiple frequency bands. And in some cases, there might need to be switching between them dynamically. So advancing these techniques and optimize and the beamformings that are required to add complexity and our current relevant research topics. So the choice between ITS and DTS architecture depends on the specific requirements of the application. ITS is better suited for environments where terrestrial infrastructure is feasible, offering lower latency and stable connectivity. DTS is ideal, though, for remote dynamic environments, providing broader coverage and independence from terrestrial infrastructure at the cost of higher technical complexity. From recent 3GPP release, so what is expected for the current next release, that is release 19, some advancements were introduced, bridging the gap between terrestrial and satellite communication systems. Some of the highlights are Storing Forward, SNF. It is designed to provide a delay-tolerant IoT communication service. This functionality allows the satellites to temporarily store data from user equipments and forward it later when the feeder link to the ground becomes available. So the idea here is that the satellite would be passing by and collecting information from different IoT users, and whenever the data, the link to the ground station becomes available, it then broadcasts to the ground station. So this is particularly useful for monitoring applications where you don't need real-time interaction. UE satellite UE communication, that is a new introduction in release 19, which bypasses the terrestrial ground network entirely. This mode avoids the limitations of long delays, lower data rates, and excessive backhaul resource consumption. So this is a notable shift from the transparent satellite access mode that was used in release 17 and 18 to a more autonomous and efficient satellite communication model. Also, another innovation here, novelty in release 19 is the GNSS independent operation. For the first time in release 19, it supports satellite access for the UEs without GNSS receivers or in environments where the GNS services are unavailable. So before, this was a prerequisite, the availability of GNSS capability in release 17 and 18, but now this is eliminated. So this feature significantly expand the reach of satellite-enabled services, particularly for IoT devices deployed in remote and challenging environments, or even satellite IoT devices that are in areas where GNSS or GPS signal is not available. And support for regenerative payload. As I mentioned in the previous cases, the 3GPP favored transparent payload, but now they are emphasizing regenerative payload. So into this release, we will introduce support for satellites with regenerative payloads, enabling 5G system functions to be implemented directly on the satellite. This means that the satellites can perform the tasks such as signal processing, reducing the dependence on ground station and enhance the system efficiency. This capability is a key enabler for improved spectral efficiency and advanced satellite-based services. And in the future, we also expect the support for reduced capability UEs, the 5G RedCap, with NRNTN. Another vital addition is supporting this RedCap UEs, and the devices are designed for mid-range IoT applications, balancing high data rates and cost efficiency. So the RedCap UVs broaden the range of the devices that can benefit from satellite connectivity, especially for use cases like industrial IoT, wearables, and smart agriculture. In summary, this release 19 represents a significant leap forward for NTNs, enhancing communication flexibility, improving system efficiency, and expanding accessibility. So next, I'll give a quick example of the impact of Doppler effects. And so the Doppler effect presents one of the most significant challenges for satellite IoT systems, particularly for the low Earth orbit. In this orbit, the satellites travel with a velocity around 27,000 kilometers per hour, and this rapid relative motion between satellites and IoT end devices causes a frequent shift in the transmit signal, impacting the communication reliability. While manageable in terrestrial networks, this effect becomes critical design consideration in satellite-based systems, in particular in DTS. So what is the Doppler effect in this case here? So the Doppler effect occurs when there is a relative motion between the transmitter and the receiver, causing a shift in the observed frequency of the signal. In the context of LEO satellites, we have two components. We have the Doppler shift, which is the same that occurs in the ground network when the objectives or when the transmitter and receiver are moving relatively to each other. So the Doppler shift is this instantaneous change in frequency experienced by a receiver at the beginning of a signal reception. However, we also have the Doppler rate, which is the time-varying frequency shift that occurs during the signal's reception due to the continual relative motion. So these are two things that we need to characterize here and that are very relevant because the satellite is traveling at a very fast speed and is changing its position, and as it changes the position, it also incurs on a time varying frequency shift. So both these components impact the ability of the IoT device to maintain a stable connection with the LEO satellites. So we have one example here. Here we have Earth and the several devices. This is the footprint of the satellite. It's connected here and is passing through this region here from right to left. So this is the travel path of the satellite. So a device that is connected here in this region with the black arrow is experiencing now high Doppler rate and low Doppler shift, and when it's in this red area. So the Doppler rate is quite significant, but the Doppler shift is very small because the device under this area is pretty much on a 90-degree angle with this satellite. So and in this position, the Doppler shift is quite small. So there is a small transition. However, the Doppler rate, it will be very large because the instantaneous variation from the signal will be very large, which can cause complications to the detection of the signal. And in the other neighboring areas, as the satellite moves, the angle between the device and the satellite then will, in this case, increase in moving towards this direction here. And then in those regions we have low Doppler rate, so the instantaneous change is small, but the high we have a high Doppler shift because this is the portion where the satellite is leaving the coverage area, and then the Doppler shift is more pronounced than the Doppler rate. So under the satellite, or if we look up and see the satellite, we will be experiencing low Doppler rate. So there is little change in the Doppler rate. We can see this here. We would have some effect similar to this. So in this case here we have the simulation time of the travel path of the device. So when we are at in the center here, it would be equivalent to being under the satellite, and then we have a large shift in terms of Doppler rate. Uh, when we are under the satellite, which is this case, but the change in frequency is very small. So that's what we are observing here. But if we are on the corners here of the network, where the elevation angle between the device and the satellite differs, then we have larger Doppler shift for these different frequencies, but the Doppler rate is quite small. So we now need to take into account these two effects of the Doppler, and then they can both contribute significantly to the frequency variation in the receiver. For instance, for this case here at 400 megahertz, we have very little Doppler shift when we are here, but the instantaneous variation here is quite significant. So it's in order of 600 hertz per second, which is quite large compared to the adaptability of the different devices. So as we mentioned, LoRa has had a support for a variation of 110, 120 hertz per second in terms of Doppler, and we exceed this easily here for 2.1 gigahertz, and it's on the margin of exceeding this tolerance by LoRa for 400 megahertz. If we are then in somewhere in between, then we will have a combination of these two effects, and we will need to see if the device is able to tolerate these high variations in terms of Doppler. So this leads to a few outages relevant to Doppler. So in LEO satellite networks, the Doppler effects they influence the communication in several ways. So one is the static Doppler shift. So at lower elevation angles, as we did, just exemplify, and maximum link distances, which would be this case here, the Doppler shift can degrade the link quality, making it difficult for the receiver to lock onto the carrier frequency. This effect is most pronounced when the satellite is near the horizon relative to the IoT device. And in the dynamic Doppler rate introduces additional challenges as the satellite moves closer to the IoT device, so higher elevation angles. The rapid variation in frequency can cause packet losses if the receiver fails to remain synchronized with the changing carrier frequency. So this is the case where the device locked the Doppler, but because we have these huge variations here, it might be hard for the device to keep synchronized, and then that will trigger a different type of error. So the Doppler effect interacts with key communication settings in particular in DTS systems, affecting their performance. In terms of bandwidth, a wider bandwidth can mitigate the impact of Doppler shifts by accommodating a broader range of frequency deviations. However, this comes at cost of increased power consumption and interference. There is also the usage of carrier frequencies. Higher frequencies experience great Doppler effects. So as you can see here from these figures, the higher the frequency, the higher the Doppler effect, and the higher the Doppler rate. And there is also the orbital height. So lower LEO satellites exacerbate the Doppler rate due to their closer proximity and faster relative motion. So if the orbit is around 500 kilometers, the effect will be larger than the effects of an orbit that is around 1,000 kilometers. However, that also comes at the cost that you have a very significant degradation in terms of path loss when you change orbits. So there is you may increase Doppler performance, but you decrease path loss. So empirical studies have provided insights into how Doppler effects influence the DTS systems, in particular for LoRa. So the Doppler shift, the signal degradation is most severe at the low elevation angles, where the relative motion is more pronounced and the satellite is at its maximum distance from the IoT device. The Doppler rate, high elevation angles where the satellite is closest to the device experience packet losses due to their rapid frequency changes, emphasizing the need for robust synchronization mechanisms. So measurement campaigns were done by NordBuy CubeSat operating at 430 megahertz. They validate these findings and demonstrations that the LoRa has a strong immunity to the Doppler effect under certain configurations. So how do we address these challenges? We need to further analysis to evaluate the performance of emerging modulations like FHSS and the interplay between the communication parameters, such as the spreading factor, the coding rate, the carrier frequencies, and how they can mitigate Doppler-induced losses. Also, there is advanced link synchronization techniques to maintain the link reliability in dynamic scenarios. And there's also potential to use precompensation mechanisms to mitigate this type of mitigate the Doppler effects. In here, we have an analysis of frequency FHSS, frequency hop spectrum. In this case here, we have success probability. So we are enabling several thousands of devices to be connected to the network and evaluate the probability of success. So for different configurations here in terms of rate. So this would be the two possible rate configurations for this setup. You can find more details on these publications. And we have here the analytical framework and also the simulation-based framework in MATLAB. But the main point of this figure here is to show that LoRa network is able to scale. So we have a very good in terms they operate in terms of reliability very well up to a few thousands of devices, and that is not possible with other solutions that are operating with even lower than 1,000 devices. So operating with very large networks with these solutions, either LoRa in this particular case with FHSS, is doable and the performance is quite reasonable. That is also supported by recent experimental results and also by our simulators. We also have done some analysis of the modeling the time and current consumption of LRFHSS. So here we have a snapshot of the transceiver operation. So here is the transceiver in sleep mode, then it wake ups. Here's the wake up signal to start transmission. There is a radio preparation phase, and then it will start the transmissions. So here we can clearly see when the headers come. So here's where the headers are transmitted, and here's when the payloads are transmitted. If you remember, the payload is transmitted over different frequencies. So over the several fragments over different frequencies. So there is the frequency hopping component, and then that's what these spikes here mean. And here we can clearly see what is the start and end of transmission and the relatively time on air. And the time on air. And with that, we can then calculate what is the current consumption for this device, and we provide an analytical model to account for the energy consumption of LRFHSS. And this was done using this module from Centec and their radio. So we did the measurements and also then provide a model for calculating the energy consumption of this type of devices. Concerning LRFHSS, so Muhammad Asad Ullah, that recently graduated, most of his works are based on a MATLAB simulator that for LoRa and for FHSS. And more recently, we built with former student Jean de Souza Santana one LRFHSS event-driven simulator that is built on Python. So these simulators, they are openly available. You can check Mohammed Assad and Jean Santana's GitHubs and have them or contribute to their development. So the main difference from this event-based type of simulator is that we have the basic functions, and then we can have additional Markov models that can be run or can be tested. So how this traffic arrives at the devices and how they are accounted for the nodes. So modeling their behavior. And then here we can have a look into the performance in terms of the number of devices and the throughput or goodput of the network for different configurations. And we are also providing potential extensions. So once we build the base setup for the simulation, we have different types of traffic that are additional libraries that we can add or functionalities that we can add to the network. And we also provide this a mechanism to allocate resources. So an asynchronous contention resolution solution that was an extension that is also available in the package. So you can use these solutions and exploit these type of simulators on your own research. We have applied the notion of direct to satellite and indirect to satellite to different scenarios. In this particular case here, we are using marine shipping in the Arctic, so in the northern sea. So we have shown these results in this magazine paper for considering situational awareness of autonomous ships in the Arctic. So we show that if we use DTS for enabling the messages for situational awareness to be broadcast from the ship to the satellites, it is doable to do it with a direct satellite connectivity using even LoRaWAN technology. And this can be further enhanced by using, for instance, FHSS type solutions. We exploit actual constellations to show that the devices will always, the vessels will always be connected to at least one satellite, even though there are more satellites in this region in a particular time. And then we can reliably connect and estimate the positions or receive the relative positions of these different devices. And in the future, using cellular type solutions, other functionalities of the situational awareness and other functionalities of the vessels can be used using the same type of approach, using direct to satellite connectivity, but then instead of LoRa, using cellular-based solutions. We also apply the same principles to other two scenarios. One is offshore wind farms. We have devices deployed in different wind farms in the coast of Denmark, and these wind farms are real. So we have their positions, their specifications of the towers, and we assume that we would be doing monitoring using monitoring of the conditioning of the maintenance of these wind farms using LoRa-based sensors. And we exploit then ITS and DTS solutions into these very large areas to see what would be the best approach in these scenarios. This is also available in this Industrial Informatics journal, where we have a little bit more results and discussing the pros and cons of these different solutions. And then more recently, we also have this underground satellite. So we had the idea is that there is possibility to connect underground sensors, so buried the devices up to 30 centimeters on the ground, and these devices would still be able to communicate with the satellite and to the ground network. So here we again compare the usage of satellite direct and indirect to satellite architectures for these remote farming scenarios where we could do monitoring of different crops and even bury the devices and still be able to connect to the satellites, advocating for the usage of the direct to satellite solutions. More recently, this is particularly a result from Konstantin and where also Assad, a former student, was involved. So the main idea here is to understand how the 6G and MDC connectivity can be enabled in remote regions with limited or no terrestrial infrastructure, and how future terrestrial or non-terrestrial MDC systems should coexist, so enabling different use cases. And then the main objective of this case here is to evince the usage of RedCap solutions. So RedCap performance in here, as you can see, we are doing the analysis of the success probability again. And here we have also this length distance of the devices and the elevation angle of the satellite. So this is where this at 9 degrees means that the satellite is on top of your on top of the device, and here is when the satellite enters into the range of line of sight to the device. So here at the top of the device there is possibility of success probability, so very high probability for different satellite heights. So there is a enhanced red cap, there is a traditional head cap. So this is the first version of red cap. This is already the increased bandwidth red cap solution. So we can see here that with different gains in terms of the antenna reception gains, we can get better performance in terms of reception. But overall, the main message is that even for low elevation angles, it is possible to establish a good connection for this technology already. So we are now studying how can we further characterize it and then exploiting the potential uh, uh, usage of RedCap solutions, RedCap as an alternative solution for NTN, NR NTN. Here is our experimental setup. So we have the rooftop of IEEE. We have an antenna deployed there that is connected to this LoDa ESP32 terminal. And with that, we can collect data regarding SNR, RSSI, and Doppler, and record this information on the dataset. There are a few constellations that are passing by OLU. Here are an example of a few of them that are broadcasting some metering information, so situational awareness type of information from the satellites. So we are collecting this transmission data plus whatever payload these devices are broadcasting, as just as a proof of concept that this can be that we can receive this, and then we can also use these measurements to do further analysis. So some future directions. So satellite IoT holds an immense promise for global connectivity. Several critical challenges, though, must be addressed first. And I would like to highlight here a couple points. One is the Doppler effect. There's very a significant decrease in performance due to the Doppler effects, and then there is need to overcome this challenge. So one of the points related to Doppler effects is the synchronization. High Doppler rates and shifts can cause frequency misalignment, leading to packet losses, advanced synchronization, then and precompensation mechanisms would be critical to address this challenge. Alternative modulations. So traditional waveforms like GMSK and OFDM may not offer sufficient robustness against Doppler variations. So further research into novel modulations or hybrid waveform designs is essential to ensure reliable communication in dynamic environments. The other point is then related to the scalability. So massive uplink management is becoming critical. The simultaneous uplink transmissions from energy-constrained devices can overwhelm satellite gateways and or G0Bs and create interference and data processing challenges. So this is something that needs to be looked at on how to manage the uplink of several thousands of devices. Advanced onboarding processing. So as we can see, the already 5G release 19 is opting for regenerative payload, and that is a trend that is expected to become even more um, used in the future, especially if we then think on higher layer functions like network virtualization and edge, so that the processing is done completely on the satellite side, on the satellite network. So you can think that the satellite is not only a hub operating and doing some of the G0B functions or full G0B functions, but the satellite constellation acts as a space edge cloud or a data processing component. So this the integration, the whole constellation becomes a processing unit, and the satellites are able then to communicate and transfer information and data and offload computing processing requests to other satellites that are in the constellation. So this is something that is being already studied, especially in concerning aspects of the networking on the satellite side. And is a quite relevant topic, matching also with the current standardization interests. And then the integration of non-terrestrial and terrestrial networks, that is as a clear challenge. How these two networks would communicate, how to do the efficient allocation between of resources across these networks and jointly do the resource allocation. So one of the fronts here is alternative waveforms, robust waveforms that can operate in both in satellite and non-terrestrial networks. So as we see that the Doppler effects, hyperfluid gains, are challenges, so it might not be ideal to have the same modulation or waveforms to communicate to satellite and also to communicate within the terrestrial networks. But this is something that needs further analysis. Adaptive modulation encoding, also schemes that are capable to operate efficiently in hybrid systems to ensure consistent performance across terrestrial and satellite systems. And then the joint resource management of these both networks. So the joint spectrum power and computational resource allocation between terrestrial and non-terrestrial networks. And also thinking about to leverage the network and the whole constellation, not only a single satellite, but how these inter-satellite links would be used and exploited into these, and how could the offloading of computational tasks could be done. Are still open challenges, and we will need lots of further research. So these innovations will enable a unified communication ecosystems, allowing IoT devices to seamlessly transition between terrestrial and satellite networks in the future, and that is one of the ultimate goals for the next generation. And the whole array for satellite IoT involves solving these challenges through advanced technologies and innovative designs, addressing Doppler effects, enhancing scalability and energy efficiency. And integrating the terrestrial and non-terrestrial networks will ensure this reliable, scalable, and global connect future for IoT. So, thank you for your attention. I hope you gather some interesting ideas from satellite IoT. If you want to know more about it, you can visit satelliteiot.org, and also you can find further details or related to these publications on my personal webpage. And if you have any questions or would like to have some ideas or interested to work on these areas, please let me know. You can always reach me by email at hirley.alves@olu.fi. So thank you.